Hello, fellow sapiens. Welcome to Sleepless Homo, where we slow everything down. Take a breath, let your mind quiet. Whether you're settling into bed, driving through the night, cooking, showering, or just working with headphones on. This is soft science, not wild speculation. Humble storytelling from archaeology, genetics, and human origin, told calmly and without drama. If you happen to drift off in the middle, don't worry. I've placed timestamps in the description so you can return the next day and continue the story from where you left it, because this one is worth hearing from beginning to end. If you find value in these long-form explorations, consider liking and subscribing. It helps this kind of careful educational work reach others who want to learn and maybe conquer the world with knowledge instead of noise. Share with me too. Do you use these episodes to fall asleep, to focus, or to travel through deep time while doing other things? Or simply tell me where you're watching from. And as always, stay curious, stay calm. Now, let's talk about the worst time to be human, 930,000 years ago. What if every human ancestor alive could fit into one apartment block? Not a city, not even a village. Just a single high-rise filled with barely more than 1,000 individuals. That image is not an exaggeration. It is one of the strangest and most sobering conclusions to come out of modern genetics, that roughly 930,000 years ago, our ancestors stood on the knife's edge of oblivion. Not almost metaphorically, not as a poetic flourish, but in the cold arithmetic of survival. Nearly 99% of the ancestral human population disappeared, leaving behind only a thread of continuity that somehow stretched across 100,000 years of scarcity and uncertainty. The astonishing part is that you are here, listening, only because that thread never snapped. The reveal came not from fossils or fragments of bone, but from the one archive that every living person still carries, DNA. Today, geneticists can use the variations in our genomes as a kind of time machine, letting us look back at the population sizes of our ancestors long before modern humans appeared. When researchers recently modelled over 3,000 genomes from people living around the globe, they discovered a dramatic bottleneck. Instead of the hundreds of thousands of breeding individuals expected for a widespread hominin population, the effective breeding population collapsed to roughly 1,280. And the astonishing part is that the bottleneck did not last a decade or even a millennium. For around 117,000 years, our ancestors remained at levels that today would qualify them as critically endangered. To grasp what that means, it helps to picture scale. 8 billion people live on Earth today. Imagine if an event, sudden or stretched across centuries, cut that number down to a single stadium of survivors. Imagine that those people then had to sustain themselves not with modern agriculture or medicine, but with the bare hands and stone tools of the deep past. That is the kind of crisis we are speaking about, and yet no stadium was ever filled. At best, one could count them into a few towers of apartments, scattered in Africa and perhaps beyond, isolated in pockets where food and water still existed. This is the first time in the story we must pause and admit uncertainty. Scientists are not sure exactly who these ancestors were. They were not Homo sapiens as we understand ourselves today. They may have been early forms of 𝐓𝐈𝐌𝐿𝐿, or another transitional lineage. The fossil record between 950,000 and 650,000 years ago is remarkably thin, almost silent, which makes it very difficult to identify the precise faces behind the numbers. But the genetic signal is there, clear and insistent. The bottleneck happened. The scale of the loss challenges our sense of continuity. We often imagine human history as an unbroken rise, one discovery building upon another until cities and satellites appear. Yet here is evidence of rupture. For more than 100 millennia, there may have been times when an entire hominin population could have been extinguished by a drought that lasted too long, or a sudden disease that passed from one clan to another. The world did not care if they lived or died, and the world almost won. What drove this collapse is still a matter of research and debate. At this point in the story, we cannot rely on one clear villain. No single eruption, no single flood or plague has been proven to align with this moment. What we can say is that the timing coincides with a period of profound climate instability, when ice sheets grew larger and cycles of cold and dryness lengthened. Africa itself, the likely centre of these populations, suffered long droughts. Habitats that once supported diverse herds of animals and wide belts of woodland shrank. Rivers dried, lakes contracted. Even for a clever and adaptable primate, food became scarce. Scarcity meant smaller groups, and smaller groups meant greater vulnerability to random chance. If a band of 30 adults lost too many hunters, or if an outbreak struck, there was no safety net. But to reduce it only to climate would be to oversimplify. The truth is that bottlenecks are rarely caused by one neat factor. Ecosystems collapse in complex ways. When prey animals declined, predators changed their ranges. When plants withered, herbivores followed shrinking green corridors, leaving hunters with little to track. Each shift cascaded into another. The bottleneck may have been the sum of 1,000 small collapses spread across generations. From the perspective of today, there is something almost haunting about how invisible this crisis is in the ground. Archaeologists look for sites filled with stone tools, hearths, and bones. Yet for this period the silence is extraordinary. It is not that no one lived, but that so few did, in so few places that traces hardly survived. This absence of evidence matches the genetic evidence. If only 1,000 breeding individuals lived, the odds of their camps being preserved and later discovered are vanishingly small. It is as if nature almost erased them from memory, leaving just enough to keep the story going. And here is where the mind turns to questions. How close did they come to absolute extinction? Could one unlucky turn, a disease, a series of bad winters, a volcanic ash cloud, have ended the entire line that eventually produced Neanderthals, Denisovans, and us? The answer has to be yes. The population was so small, so precariously balanced, that even a minor disruption might have tipped the scales. That we are here at all suggests resilience, but also sheer luck. For scientists, reconstructing this story is an act of humility. The numbers may feel precise: 1,280 survivors, 98.7% loss, but they are still approximations drawn from models and assumptions. What matters most is not the exact figure but the magnitude of the collapse. The human line almost ended, and it stayed almost ended for longer than the entire span of Homo sapiens so far. Our species is only about 300,000 years old. This bottleneck lasted 100,000 years, a third of that span when nothing was guaranteed. In this light, the image of that single apartment block full of survivors becomes not just a metaphor, but a kind of anchor. Imagine peering through time and seeing them, scattered bands of foragers across Africa, each group a single floor of that imaginary tower. They had no way of knowing they were holding the fate of the species. They simply hunted, gathered, sheltered, raised children, and died. From their perspective, nothing was extraordinary. From ours, everything was at stake. It is tempting to look for heroes in this story, to imagine that those who survived were somehow stronger, smarter, more adaptable. Perhaps they were. Perhaps they had habits or technologies that gave them a slim edge. But it may also have been geography, chance, or even sheer fortune. A river that did not dry, a herd that returned, a cave that stayed dry. Extinction is not always about weakness. Survival is not always about superiority. It is often about being in the right place at the right time. What we are left with, then, is a sense of fragility. The great human story, so often told as triumph, began with a near erasure. And perhaps that is fitting. Every future invention, every city, every piece of art or science depended first on that fragile continuity. Without those 1,000 ancestors, none of it would have happened. In a strange way, it was the worst time to be human and the most important. For in enduring it, our ancestors proved that the line could bend but not always break. The haunting question that lingers is simple. If we almost vanished once, could it happen again? That is not a question this chapter can answer. It is only one to carry forward. For now, the image remains. One apartment block filled with the last humans living through the day the numbers broke. Why did ice sheets suddenly shift from rhythms of 41,000 years to ones lasting 100,000 years? That question still unsettles climate scientists today. because it marks one of the most dramatic reorganizations of Earth's climate system in the last 2.5 million years. The world our ancestors walked through 2 million years ago was already an ice age, but not the kind of unrelenting frozen planet people sometimes imagine. The ice age was a rhythm, a long dance between glacial advances and warmer interludes, a pattern written not by chance but by the mechanics of Earth's orbit around the Sun. For nearly a million years that rhythm was predictable, ticking at intervals of 41,000 years. Then something changed. Ice sheets grew larger, cycles stretched longer, and the climate swung harder. This was the 100,000-year problem, and though we know it happened, the precise reasons remain elusive. To understand this, we need to step back and imagine Earth as a planet constantly shifting under astronomical nudges. The cycles that pace the Ice Age are called Milankovitch cycles, after the Serbian mathematician who refined their study in the early 20th century. They are the slow variations in the shape of Earth's orbit, the tilt of its axis, and the wobble of that tilt. None of them are fast by human standards. They play out across tens of thousands of years, yet combined, they control how much solar energy reaches the planet's surface, particularly in the high latitudes where ice sheets grow or melt. Small changes in the timing and intensity of sunlight can decide whether snow survives the summer and accumulates into glaciers or whether it melts away. Over millions of years, this dance of sunlight and ice produced the alternating warm and cold periods that defined the Quaternary period. For much of the early Quaternary, from about 2.5 million years ago to 1 million years ago, the pattern was dominated by Earth's axial tilt, which oscillates every 41,000 years. When the tilt is greater, summers are stronger, melting more ice. When the tilt is less, summers are weaker, allowing ice to persist. This made the Ice Age cycles relatively short and by later standards relatively mild. Ice sheets waxed and waned, but they were thinner and shorter lived compared to what followed. For our early hominin ancestors, this meant climates that were challenging but not catastrophic, with African landscapes alternating between wetter and drier states at a manageable tempo. Then, around 1,100,000 years ago, the system changed. The cycles lengthened to roughly 100,000 years, and their intensity increased. Ice sheets grew thicker and more extensive. Cold periods lasted longer. Warm interludes became shorter and less forgiving. The climate system had entered what scientists now call the Middle Pleistocene transition. Why the rhythm changed is still one of the great unsolved questions in paleoclimatology. One possibility is that the gradual cooling of the planet over millions of years crossed a threshold. Before the transition, thin ice sheets would respond quickly to changes in tilt, melting away when summers warmed. But as the background climate cooled, ice sheets became thicker and more stable. They no longer disappeared completely in warm phases. Instead, they persisted, amplifying the importance of the slower orbital cycles, particularly changes in eccentricity, the shape of Earth's orbit, which runs on a 100,000-year scale. This may have locked the climate into its new rhythm. Another idea is that geology played a role. Ice sheets grind down bedrock as they grow, scraping away soil and leaving behind hard, reflective surfaces. Over time, this removal of regolith could have changed how ice interacted with the land, making it harder for ice to retreat and easier for it to advance further during each cycle. If that is true, the transition was not just an astronomical inevitability, but a feedback between ice, rock, and climate. We also know that carbon dioxide levels were gradually declining across the early Pleistocene. Lower greenhouse gas concentrations would have reduced the planet's baseline warmth, making it easier for ice to expand and harder for it to retreat. This may have amplified the effect of orbital changes, deepening the glacial periods. Yet when scientists examine ice core records, the changes in carbon dioxide seem too small to explain the full force of the transition, suggesting that multiple factors must have worked together. Why did ice sheets suddenly shift from rhythms of 41,000 years to ones lasting 100,000 years? That question still unsettles climate scientists today, because it marks one of the most dramatic reorganizations of Earth's climate system in the last 2.5 million years. The world our ancestors walked through 2 million years ago was already an ice age, but not the kind of unrelenting frozen planet people sometimes imagine. The Ice Age was a rhythm, a long dance between glacial advances and warmer interludes, a pattern written not by chance but by the mechanics of Earth's orbit around the Sun. For nearly 1 million years that rhythm was predictable, ticking at intervals of 41,000 years. Then something changed. Ice sheets grew larger, cycles stretched longer, and the climate swung harder. This was the 100,000-year problem, and though we know it happened, the precise reasons remain elusive. To understand this, we need to step back and imagine Earth as a planet constantly shifting under astronomical nudges. The cycles that pace the Ice Age are called Milankovitch cycles, after the Serbian mathematician who refined their study in the early 20th century. They are the slow variations in the shape of Earth's orbit, the tilt of its axis, and the wobble of that tilt. None of them are fast by human standards. They play out across tens of thousands of years, yet combined, they control how much solar energy reaches the planet's surface, particularly in the high latitudes where ice sheets grow or melt. Small changes in the timing and intensity of sunlight can decide whether snow survives the summer and accumulates into glaciers, or whether it melts away. Over millions of years, this dance of sunlight and ice produced the alternating warm and cold periods that defined the Quaternary period. For much of the early Quaternary, from about 2.5 million years ago to 1 million years ago, the pattern was dominated by Earth's axial tilt, which oscillates every 41,000 years. When the tilt is greater, summers are stronger, melting more ice. When the tilt is less, summers are weaker, allowing ice to persist. This made the Ice Age cycles relatively short and by later standards relatively mild. Ice sheets waxed and waned, but they were thinner and shorter lived compared to what followed. For our early hominin ancestors, this meant climates that were challenging but not catastrophic, with African landscapes alternating between wetter and drier states at a manageable tempo. Then, around 1,100,000 years ago, the system changed. The cycles lengthened to roughly 100,000 years, and their intensity increased. Ice sheets grew thicker and more extensive. Cold periods lasted longer. Warm interludes became shorter and less forgiving. The climate system had entered what scientists now call the Middle Pleistocene transition. Why the rhythm changed is still one of the great unsolved questions in paleoclimatology. One possibility is that the gradual cooling of the planet over millions of years crossed a threshold. Before the transition, thin ice sheets would respond quickly to changes in tilt, melting away when summers warmed. But as the background climate cooled, ice sheets became thicker and more stable. They no longer disappeared completely in warm phases. Instead, they persisted, amplifying the importance of the slower orbital cycles, particularly changes in eccentricity, the shape of Earth's orbit, which runs on a 100,000-year scale. This may have locked the climate into its new rhythm. Another idea is that geology played a role. Ice sheets grind down bedrock as they grow, scraping away soil and leaving behind hard, reflective surfaces. Over time, this removal of regolith could have changed how ice interacted with the land, making it harder for ice to retreat and easier for it to advance further during each cycle. If that is true, the transition was not just an astronomical inevitability, but a feedback between ice, rock, and climate. We also know that carbon dioxide levels were gradually declining across the early Pleistocene. Lower greenhouse gas concentrations would have reduced the planet's baseline warmth, making it easier for ice to expand and harder for it to retreat. This may have amplified the effect of orbital changes, deepening the glacial periods. Yet when scientists examine ice core records, the changes in carbon dioxide seem too small to explain the full force of the transition, suggesting that multiple factors must have worked together. How can the DNA of living people reveal a near extinction from almost 1 million years ago? It sounds impossible at first glance. After all, genes do not come with timestamps like fossils buried in the ground. Yet in 2023, a team of researchers showed that by looking closely at the genetic variation among modern humans, we can reconstruct episodes of our deep past that left no clear trace in stone or bone. What they uncovered was startling. Evidence that our ancestors dwindled to barely over 1,000 breeding individuals around 930,000 years ago, and that this precarious state lasted for more than 100,000 years. The discovery did not come from a cave or an excavation site, but from a method with the somewhat intimidating name of fast infinitesimal time coalescent, or 𝐓𝐈𝐌𝐿. The idea behind this approach is deceptively simple, though the mathematics behind it are anything but. Every human genome carries countless tiny variations. These variations arise from mutations, small changes in DNA that occur from generation to generation. Over time, the number and distribution of these mutations reflect the size and history of a population. In large populations, more variation accumulates because more people are passing on mutations. In small populations, fewer lineages mean fewer mutations survive and variation shrinks. By carefully analysing patterns of variation in thousands of people alive today, scientists can rewind the genetic clock, reconstructing how population sizes must have changed over hundreds of thousands of years. The team behind the 2023 study analysed more than 3,000 complete genomes from 50 populations worldwide, including 10 from Africa and 40 from other regions. They applied the FITCOAL model, which allows for the detection of very ancient demographic events with higher precision than earlier methods. Unlike older coalescent approaches that examine changes in broader strokes, 𝐓𝐈𝐌𝐿 breaks down the evolutionary timeline into tiny increments, allowing scientists to spot shifts that occurred far back in time. The result was a sharp, unmistakable signal between about 930,000 years ago and 813,000 years ago. The effective population of our ancestors plunged to roughly 1,280 breeding individuals. The term effective population size requires some explanation. It is not the same as the head count of everyone alive at a given moment. It is a genetic measure that reflects how many individuals are contributing their DNA to future generations. In a highly structured or fragmented population, the effective number can be smaller than the census number. But even with that caveat, the collapse revealed by 𝐓𝐈𝐌𝐿 was severe. 98.7% of the ancestral population vanished in the models. The survivors were few enough that they would have fit into a modern town hall. It is important to pause here to consider why such genetic detective work is necessary. The fossil record for the period between 950,000 and 650,000 years ago is exceptionally sparse. Archaeologists sometimes refer to it as a kind of ghost interval. Very few bones have been found, and these stone tool assemblages are scattered and ambiguous. Traditional archaeology alone could not have told us whether a near extinction happened. The genes, however, remain in every cell. They are silent records of who made it through, and in this case they are far more complete than the ground beneath our feet. The 𝐓𝐈𝐌𝐿 study also emphasised how long the bottleneck lasted. One might imagine a sudden catastrophe that decimated a population, but was quickly overcome. What the genomes suggest instead is something more drawn out, a sustained reduction that lasted more than 100,000 years. That means generation after generation, for longer than Homo sapiens have yet existed, our ancestors were surviving at levels close to extinction. This alone forces us to rethink how resilient small populations can be, but also how vulnerable they remain. One of the striking aspects of this research is that it shows how similar we all are today. Compared to chimpanzees or gorillas, modern humans are remarkably uniform genetically. Two chimps from different forests in Central Africa may be more genetically distinct from one another than any two people living continents apart. This low diversity has long been recognised, but 𝐓𝐈𝐿 helped explain one of the reasons why. A deep bottleneck left only a narrow sliver of ancestral variation, and we all descend from it. That is why you can take DNA from people across the globe and still find such small differences. The bottleneck pruned the tree of human ancestry to a few surviving branches. Of course, science is cautious by nature, and the researchers themselves stressed the limits of their work. 𝐓𝐈𝐌𝐿 is a model. Like all models, it makes assumptions. The exact numbers may shift as new data and methods appear. Some critics argue that the bottleneck might have occurred earlier than 930,000 years ago, or that the severity could be less extreme. Others suggest that what the model is picking up may be a combination of events rather than a single drawn-out collapse. These debates are healthy. They remind us that we're not staring into a clear window on the past, but rather piecing together signals filtered through time. What makes this work so valuable is not the illusion of certainty, but the ability to pose sharper questions. Without genetics, we might not even suspect that our ancestors nearly vanished. With genetics, we can test new hypotheses about why, when, and how. Was the bottleneck caused by environmental shifts? Was it tied to changes in food availability, migrations, or diseases? We cannot yet say. But we know the collapse was real enough to shape the course of hominin evolution. It is also worth emphasizing that this was not a story of one location. The genomes sampled came from populations across Africa and beyond, and yet the signal was global. That suggests that the bottleneck affected the entire ancestral population, not just one region. The survivors, wherever they lived, carried the genetic legacy forward. All modern humans, Neanderthals and Denisovans, may ultimately trace back to those scattered groups. The study authors even speculated that this bottleneck might coincide with the emergence of a common ancestor of those later lineages, though that remains a hypothesis, not a conclusion. For listeners, the most fascinating part may be the method itself. It is almost magical to imagine that by analysing DNA from people alive today, we can reach back nearly 1 million years. Yet it is not magic. It is mathematics applied to biology, careful comparisons of mutations and their frequencies. Each mutation is like a tiny timestamp, telling us when lineages diverged or converged. Collect enough of them, and the patterns reveal population history. 𝐓𝐈𝐿𝐾𝐒 simply sharpened the focus, giving us a clearer glimpse of events that older tools could not resolve. There is something humbling in this. Our bodies carry history whether we know it or not. Every cell contains a library of survival, and in this case, the story it told was not triumphant but precarious. We are here because our ancestors endured through a bottleneck so severe it could easily have erased the line. They left no chronicles, no monuments, not even many bones. Yet their story is still written in us. And here lies the haunting question. If DNA can reveal a collapse so ancient, how many other episodes lie hidden in our genomes, waiting for methods sophisticated enough to read them? We may only be at the beginning of understanding how fragile our deep past really was. Why do archaeology and fossils almost vanish during this span between 950,000 and 650,000 years ago? It is one of the strangest puzzles in the study of our deep past. For long stretches of prehistory, the Earth has been generous. We find layers of tools, scattered bones, hearths, and even footprints that tell us where hominins walked and how they lived. Then, for this interval of nearly 300,000 years, the record thins dramatically. Sites are rare, bones are scarce, and whole regions that once seemed alive with activity fall silent. To many scientists, this is not just a gap in discovery. It looks like evidence of a genuine collapse, a disappearance written not in words but in the absence of words, an emptiness where voices should be. The reveal is unsettling. When archaeologists lay out timelines of stone tool industries, they expect to see continuity. The older one tradition, then Acheulean hand axes, then gradual refinement. Instead, what we find across this interval is fragmentation. In Africa, Europe and Asia alike, the archaeological visibility of our ancestors dwindles. Entire centuries pass with little to show. The few tools we do find are often scattered, crude, or isolated, not part of rich camps or stratified layers. The bones that could confirm who made them are rarer still. To anyone mapping the progress of early humans, this looks like the line faltering. Part of this silence may reflect preservation. Fossils are fragile, and most organisms that ever lived left no trace at all. Stone tools survive better, but even they can be eroded, buried too deep, or ground away by shifting soils. So we must be careful not to mistake absence for proof of absence. Yet when absence persists across continents, over hundreds of thousands of years, it demands attention. The simplest explanation is that there were fewer people, living in fewer places, making fewer things to leave behind. And this aligns disturbingly well with the genetic evidence that shows a severe population bottleneck in this exact window. Consider Africa, long regarded as the central stage of hominin evolution. From earlier periods, we have abundant evidence of activity. Stone tools scattered along ancient lake shores, animal bones marked with cut marks, even entire sites that look like hunting grounds. Yet during the span around 900,000 years ago, those rich sites thin. The long sequence of Acheulean hand axes shows gaps. Regions that once sustained hominin presence seem deserted. Some paleoanthropologists describe this as a desert of evidence, not because no one was there at all, but because so few were. In Europe, the picture is even starker. Early arrivals such as Homo antecessor left traces in Spain close to 1 million years ago. Then, silence. For hundreds of millennia, the continent seems almost empty of humans. A handful of tools, a tooth here, a bone fragment there, but little more. This is not the flourishing, spreading humanity we see later. It is a marginal, flickering presence, so thin that it might have winked out entirely at any moment. Asia too shows similar interruptions. Some sites in China and the Levant preserve activity earlier than 900,000 years ago, but later layers vanish or become ambiguous. The absence is not only in bones and tools, but in variety. When populations are healthy, we expect to see diversity in technology and adaptation. Different groups in different regions experiment with different strategies. During this interval, that variation shrinks. What we do find looks monotonous, as if only a few groups carried on simple traditions with little innovation. This is another clue that numbers were low, and that communities were isolated with little contact. Innovation spreads best when people are numerous and connected. Isolation breeds stagnation. It is worth asking whether we are being misled by chance. Archaeology is always incomplete. Perhaps we simply have not looked in the right places. Perhaps erosion removed crucial layers. Perhaps dense forests or deserts have hidden sites from us. All of this is possible, but the consistency of the silence across continents and its alignment with the genetic bottleneck makes it hard to dismiss as coincidence. It may truly represent a time when hominins teetered on the edge of disappearance, leaving only faint whispers of their presence behind. To imagine what this meant in daily life, picture a continent where once there were dozens of bands of hunters and gatherers moving with the seasons. Now there are only a few, scattered far apart with little chance of meeting. Children grow up never seeing another band outside their own. Knowledge cannot spread easily. If a tool-making trick or a clever hunting method emerges in one group, it may die with them, never passed on. The archaeological silence is not just about missing bones. It is about missing voices, missing connections, missing possibilities. This silence challenges us as scientists. We rely on physical remains to reconstruct behaviour, and when those remains thin, our stories become tentative. We must resist the urge to fill the gaps with speculation. Instead, we admit what we know, that the period between 900,000 and 600,000 years ago is poorly represented in the archaeological record. We can link this to the genetic bottleneck and propose that low population sizes explain the scarcity. But beyond that, we must remain humble. There may be sites yet undiscovered that will change the picture entirely, or the silence may prove real, a true reflection of a world where humans were rare, almost absent. One haunting implication of this gap is that cultural memory itself may have fractured. In later periods, stone tool traditions persist for hundreds of thousands of years, evidence of continuity. Here, continuity looks broken. If our ancestors nearly disappeared, they may also have nearly forgotten. Skills and traditions that once seemed permanent could have vanished with the groups that held them. What survived might have been a pared-down toolkit, just enough to endure. From that narrow base, later complexity would have to build again. In this sense, the silence is not just about the past, but about the fragility of knowledge itself. When we walk into a museum and look at rows of hand axes or flaked cores, we are seeing the survivors of history. The missing tools, the missing bones, the missing innovations are invisible, but no less real. They are the negative space in our story, and sometimes negative space tells as much as what is present. The silence in the stones speaks of a humanity so reduced that it barely registered on the geological canvas. And so the haunting question remains. If we had dug into the earth and found nothing from this interval, would we even have known that humans were alive then at all? Without the luck of a few fossils, without the signal in our DNA, the story might have been erased entirely. That fragility should give us pause. The human journey is not a steady march of progress, but a precarious thread, visible in one place, lost in another, sometimes almost severed. The silence is part of the story. How does a species survive stuck at endangered levels for 100,000 years? Modern conservation biology tells us that when populations fall below a few thousand breeding individuals, extinction is usually a matter of time. Random disease outbreaks, inbreeding, environmental shocks, or even bad luck can erase the last survivors. Yet around 930,000 years ago, our ancestors found themselves trapped at just such a low point. And according to genetic models published in 2023, they remained there not for a decade or a century, but for 117,000 years. The persistence of this near-extinction state is one of the strangest and most humbling stories in human prehistory. The reveal is stark. We are used to thinking of bottlenecks as brief crises. A volcanic eruption, a drought, or a catastrophe might knock numbers down, but recovery usually follows within a few generations. Here, the recovery never came, not for longer than Homo sapiens have yet existed. For 100,000 years, our ancestral line was reduced to what today would be considered critically endangered. That means each generation, stretching across thousands of centuries, lived with the constant risk of being the last. The fact that they were not is a testament both to resilience and to the sheer improbability of survival. To imagine what that meant, picture a world where the entire population could fit into a single valley. Groups may have been scattered across Africa and perhaps into Western Eurasia, but their total number was small enough that if you gathered every family together, they might have filled only a handful of modern villages. Children grew up never knowing of the other groups who shared their fate. Entire lifetimes could pass without two bands ever crossing paths. Knowledge, language, and culture were fragile things, easily lost if a few elders died. The concept of effective population size helps us grasp the scale. Geneticists estimate that the number of individuals actually passing on genes was around 1,280. The real head count may have been somewhat larger, but even if doubled or tripled, it remained dangerously low. Small populations are vulnerable to inbreeding, which reduces genetic diversity and makes them less able to cope with disease or environmental change. They are also vulnerable to chance. A flood, a fire, or a bad hunting season can wipe out a whole band, and with so few bands to begin with, each loss matters. What allowed our ancestors to endure in such small numbers? We do not know for certain, but clues lie in what we understand from modern ecology. Small populations sometimes survive, not by thriving, but by retreating into refugia, pockets of habitat where conditions remain stable enough to sustain life, while the broader environment deteriorates. In Africa, these refugia may have been river valleys that did not dry up entirely, or coastal areas where shellfish provided food when grazing animals vanished inland. These safe havens could have supported scattered groups through the harshest intervals, keeping the lineage alive even if reduced to a shadow of its former presence. Life at such low numbers must have been precarious. Social structures may have been fragile. If one group collapsed, its knowledge and traditions collapsed with it. If another survived, it carried the thread forward. The archaeological silence of this period, with so few tools or bones preserved, may reflect not only scarcity of people, but scarcity of innovation. Small groups simply did not have the population base to sustain wide experimentation or technological diversity. They may have relied on simple, familiar tools that required little teaching. In this sense, the bottleneck was cultural as well as biological. Another way to think about this is through the lens of probability. Biologists studying endangered species know that small populations can persist for surprising lengths of time by chance alone. A handful of individuals may keep reproducing just enough to offset losses, generation after generation. Eventually, if conditions improve, the population can recover. If conditions do not improve, extinction becomes almost inevitable. For our ancestors, conditions must have been just good enough in just enough places to prevent total collapse. The odds were long, but they were not zero, and so they endured. What makes the duration so extraordinary is that it was not a momentary dip, but a long plateau. Genetic reconstruction suggests that the low numbers persisted across dozens of glacial cycles. That means our ancestors were born into scarcity, lived their entire lives in scarcity, and died leaving behind children who knew nothing else. For them, precariousness was normal. They had no sense that they were rare. They simply were. From our perspective, the implications are profound. Modern humans often marvel at our species' expansion and dominance, but this history reminds us that we descend from survivors who lived in the shadow of disappearance. Every human alive today carries the legacy of that bottleneck in their DNA, a narrow genetic variation that reflects the small number of ancestors who passed through. This may help explain why humans are so genetically uniform compared to other great apes. Our line passed through a filter that removed most variation, leaving only the diversity carried by a tiny remnant. And yet, despite this uniformity, we did not vanish. Why? That question still lingers. Perhaps it was resilience in the face of hardship. Perhaps it was geography, with some bands lucky enough to occupy refuges that remained productive. Perhaps it was pure chance, the unpredictable roll of ecological dice. Whatever the answer, the outcome was that 1,000 individuals managed to sustain a lineage through 100,000 years of scarcity, long enough for conditions to shift and populations to expand again. It is difficult to compare this endurance to anything in the modern world. Conservationists struggle to maintain species with far larger populations. Some species with tens of thousands of individuals still collapse within centuries. That our ancestors endured so long at such low numbers challenges assumptions about what is possible. It suggests that cultural factors, even if minimal, may have given them a small edge. The ability to cooperate, to share food, to protect one another from predators, might have made survival at low density more sustainable than it would be for other animals. Humans are not the strongest or the fastest, but they are social, and in times of scarcity, social bonds may have been the difference between life and death. Still, we must be cautious not to romanticize. These were not triumphant survivors, but vulnerable groups living at the mercy of their environments. Their lives were likely short and filled with uncertainty. Infant mortality would have been high. Illnesses and injuries that today are minor would have been fatal. Famine and drought would have tested them constantly. There was no guarantee that the lineage would continue. From the long view of history, the remarkable thing is not that they lived well, but that they lived at all. For scientists, the bottleneck's length is perhaps the most important clue. It implies that something in the global environment created a prolonged period of difficulty. Later sections of this story will explore the potential climate drivers, but here we can only note the correlation. The world was unstable, and humans were fragile within it. The fact that numbers did not rebound quickly suggests that the pressure was continuous, not a one-time catastrophe. The haunting question that remains is how close extinction truly was. Could one unlucky century have ended the story? If one disease had spread through a few small groups, would there have been anyone left? We cannot know. What we can say is that the persistence of a lineage across 100,000 years of endangerment is one of the most improbable achievements in natural history. It reminds us that our existence is not inevitable, but contingent. Had the scales tipped slightly differently, there might be no humans to ask these questions at all. What flipped Earth's climate switch? Around 1.2 million to 700,000 years ago, the planet underwent a profound transformation that scientists call the Middle Pleistocene transition. For hundreds of thousands of years before, the climate had moved in a steady rhythm, with the ice sheets waxing and waning on a cycle of about 41,000 years. These were intense swings, but they were relatively short, allowing ecosystems and the species within them to recover more quickly. Then the rhythm shifted. The cycles lengthened to about 100,000 years. Ice sheets grew larger and more persistent, and cold phases lasted longer than any living creature had ever experienced. This was not just a change of tempo, but a change of character, a climatic trap that would test every species alive, including the early ancestors of humans. The reveal came from ocean sediments and isotopic records. Tiny organisms that lived in the sea built shells of calcium carbonate, and the ratio of oxygen isotopes in those shells reflected the volume of global ice and the temperature of the oceans at the time. When geologists drilled cores from the seafloor and lined up these isotope records across millions of years, they saw the shift clearly. Before about 1 million years ago, the cycles of glaciation were regular, paced by the tilt of Earth's axis. Afterward, the pattern changed, dominated by eccentricity, the slow variation in the shape of Earth's orbit that runs on 100,000-year intervals. The ice grew thicker, the cold phases longer, and the warm periods shorter and less forgiving. Why this happened is still debated. One explanation is that ice sheets themselves evolved. In earlier periods, thin ice sheets formed and melted easily, responding quickly to changes in solar input. Over time, as the planet cooled, those sheets grew thicker and more deeply rooted. They scraped away soils, leaving behind bare rock that allowed ice to grip more firmly. With this new stability, ice sheets no longer disappeared completely during warm phases. Instead, they persisted and expanded further during cold phases, reinforcing the dominance of the longer cycles. In this way, the climate may have crossed a threshold, tipping into a new mode that locked the world into harsher rhythms. Another factor may have been the slow decline of atmospheric carbon dioxide. Measurements from ancient air bubbles trapped in Antarctic ice cores, although not reaching back the full span of the transition, suggest that greenhouse gas levels were falling across the early Pleistocene. Lower carbon dioxide meant less background warmth, which made it easier for ice sheets to grow and harder for them to retreat. The precise numbers are uncertain, but the trend is clear enough to suggest that greenhouse gases played a role in the shift. The consequences of this transition were global. Africa, the cradle of early humans, experienced extended droughts. Large lakes that had once filled the Rift Valley contracted or disappeared entirely. Grasslands expanded and contracted in longer, harsher pulses, pushing animals to migrate vast distances or vanish altogether. Savannas replaced forests, then gave way to near desert, only to swing back again. For hominins depending on stable sources of water and food, these shifts were devastating. Entire regions that had once been habitable became barren for centuries or millennia at a time. Groups had to move, adapt, or die. Eurasia too saw landscapes transformed. Europe was scoured by advancing glaciers that reached further south than before, while Asia's interior became more arid, with deserts expanding and rainfall patterns disrupted. Species that had once thrived in milder climates now faced long stretches of cold and drought. Migration corridors that allowed animals and humans to move between continents closed or became treacherous. In this sense, the Middle Pleistocene transition did not just alter the climate, it reshaped the geography of survival. For marine ecosystems, the changes were equally dramatic. Ocean circulation patterns shifted, oxygen levels fluctuated, and many species of fish and marine mammals faced new stresses. Coral reefs declined in some areas, while plankton communities reorganized. These changes rippled up the food chain, affecting the availability of resources for coastal species on land as well. The transition was a planetary event, touching every biome and every lineage. Scientists sometimes describe this period as a retuning of Earth's climate engine. The orbital cycles that had always been there did not change, but the way the planet responded to them did. The 100,000-year rhythm that emerged has dominated ever since, pacing the great ice ages and interglacials that shaped human evolution. The ice sheets of the last glacial maximum, covering much of North America and northern Europe, were products of this new system. The relatively short warm interval we live in today, the Holocene, is just another brief interglacial within that framework. For early humans, the transition was not an abstract puzzle of orbital mechanics. It was a lived reality of scarcity, unpredictability, and danger. Where once environments might have recovered within a few centuries, now they could remain barren for tens of thousands of years. The familiar landscapes of parents and grandparents might not return within the memory of countless generations. This forced mobility and created isolation, as groups that could once reconnect after shorter intervals were now divided for entire epochs. The haunting part of this story is that it helps explain why our ancestors nearly vanished around 930,000 years ago. The bottleneck described by genetic evidence occurred within the heart of this climatic trap. The world had changed its rules, and humans were caught in the shift. Survival was possible, but only barely, and for 100,000 years they lingered in the shadow of extinction. The resolution is not that we fully understand the Middle Pleistocene transition. We do not. The precise combination of factors that flipped Earth's climate switch remains uncertain. Perhaps it was the slow grinding away of soil under ice sheets, Perhaps it was the gradual drawdown of greenhouse gases. Perhaps it was feedbacks in ocean circulation that locked in longer cold spells. Most likely it was all of these at once, converging to push the climate into a new regime. What we know is that the shift happened, it lasted, and it shaped the evolutionary path of our species. The haunting question that lingers is whether Earth's climate might flip its rhythm again. If one threshold was crossed 1 million years ago, could another lie ahead? We cannot know, but the lesson of the Middle Pleistocene transition is that the planet is not static. It is capable of reorganizing itself in ways that transform the possibilities of life. And once the switch is flipped, the new rules can last for hundreds of thousands of years. What happens when the rivers and lakes of East Africa vanish for centuries? To us, water shortages are measured in seasons or at most decades. To early hominins living through the early to middle Pleistocene transition, scarcity stretched across millennia. East Africa, long a fertile cradle of life, shifted into prolonged droughts so severe that they changed not just the landscape, but the very course of human evolution. These were not short interruptions in abundance, but mega-droughts, episodes of dryness that lasted long enough to transform entire ecosystems, drive animals to extinction or migration, and leave small, scattered bands of humans clinging to survival. The reveal is drawn from geology as much as from archaeology. Lake basins in East Africa preserve sedimentary records that act as chronicles of climate. By drilling cores and analysing chemical signatures, scientists can reconstruct when lakes were deep and full and when they shrank or vanished altogether. Around 900,000 years ago, these records show extended intervals, where lakes dried down to saline puddles or disappeared completely. What had once been lush corridors filled with fish, hippos and crocodiles became dust bowls, barren and hostile to most large animals. Rivers that had sustained human ancestors for countless generations ceased to flow. Entire valleys turned into expanses of cracked earth. One of the clearest cases is Lake Malawi. Today it is one of the largest freshwater bodies in Africa, stretching hundreds of kilometres and supporting millions of people. But sediment cores show that in the deep past, particularly between about 1 million and 600,000 years ago, it underwent repeated near-total desiccations. For centuries at a time, the basin was nearly dry, leaving behind layers of dust instead of aquatic fossils. Similar stories come from Lake Tanganyika and the smaller lakes scattered across the Rift Valley. Together, these records paint a picture of a region in flux, swinging between fertile abundance and catastrophic drought. For hominins, these changes were devastating. Water was not just for drinking. Lakes and rivers concentrated animals and plants, creating reliable food sources. When waters receded, fish were gone, hippos retreated and grazing herds moved away. Vegetation changed as well. Wet-adapted forests and woodlands shrank, replaced by open savannas or even semi-desert. Fruits, tubers and edible plants that had been staples disappeared. Groups that had learned to rely on lake margins and riverbanks suddenly faced landscapes with little to offer. The pressure on survival must have been relentless. The question is how groups endured. One possibility is that they followed the shrinking water, moving as lakes contracted to find the last remnants of wetlands. Another is that they sought refuge in areas that retained water longer, such as highland regions or along perennial springs. These refugia would have been lifelines, sustaining small populations even when the broader landscape collapsed. But such refugees could not support large numbers. They explain why our ancestors survived, but also why their populations were so small for so long. The geological evidence shows that these droughts were not uniform. They came in pulses, some lasting thousands of years, others longer. Between them, wetter intervals allowed for temporary recoveries. Lakes refilled, animals returned, and plant life flourished. But these respites were always temporary, and the cycle of drought resumed. For humans, this meant a life of constant adaptation. No strategy could be permanent. Groups had to adjust again and again, learning to live in abundance and in scarcity, in green valleys and barren plains. Those that could not move or adapt vanished from the record. What is striking is how these shifts may have influenced not just survival, but evolution. Environmental variability has long been proposed as a driver of human adaptability. When conditions change rapidly and repeatedly, species that can adjust have an advantage. In Africa, during the Middle Pleistocene transition, adaptability was not optional. It was the difference between life and death. This may help explain why later humans developed such behavioural flexibility, able to exploit many environments. The crucible of repeated droughts selected for resilience. Still, we must avoid overconfidence. We do not know exactly how small groups managed to survive. We can only infer from the evidence of drying lakes, shifting vegetation, and animal migrations. The archaeological record is thin, offering only scattered tools and bones. Yet the silence of the record is itself telling. Few sites survived because few people left traces to begin with. When populations are low and scattered, the odds of finding evidence centuries later plummet. This fits the genetic signal of a bottleneck. Droughts thinned numbers, and only a handful of groups carried the lineage forward. These mega-droughts also changed Africa's geography of opportunity. In wetter times, corridors connected different regions, allowing animals and humans to move and mix. In dry times, barriers rose. Deserts and barren plains cut groups off from one another. Isolation may have led to fragmentation, with small bands evolving separately, though only some lineages survived. Connectivity and disconnection alternated, shaping the genetic and cultural diversity of hominins. In this sense, droughts were not just crises, but forces of change, redirecting the pathways of migration and adaptation. The haunting aspect of this story is its scale. Imagine a child born beside a shrinking lake. Her parents tell her that the water used to be vast, filled with fish. She grows old watching the shoreline retreat further each year, and by the time she dies, the lake is a salt pan. Her grandchildren never see it full. For them, drought is not an event but the world itself. Multiply that across 100,000 years, and you begin to grasp the magnitude of the trap. This was not a single disaster, but a way of life. A cycle that forced humans to exist at the edge of endurance. And so the question remains, how close did these droughts come to ending the story altogether? If one last refuge had failed, would the lineage have vanished? We cannot answer with certainty. What we know is that Africa's climate was a gauntlet, and our ancestors walked it with fewer numbers than almost any species could survive. The fact that they did is remarkable, but the lesson is not triumphalism, it is humility. Our existence rests on the fragile continuity of groups who clung to the last drops of water in a drying world. Was Eurasia an escape or a trap? When Africa's lakes dried and savannas cracked under sun and dust during the early to middle Pleistocene transition, some hominins likely moved northward or eastward, seeking more stable environments beyond the equator. On the surface, this seems logical. If one region suffers drought, perhaps another offers refuge. Yet Eurasia, during the span from 1.2 million to 700,000 years ago, was no land of safety. It was a shifting frontier of glaciers, steppes, deserts, and cold winds. For hominins stepping into that vastness, survival was never guaranteed, and often the costs outweighed the promise. The reveal of Eurasia's harshness comes from both geology and archaeology. In Europe, evidence shows that glaciations advanced further south than before. Sheets of ice expanded across Scandinavia, the British Isles, and into the heart of the continent, covering fertile ground under kilometres of ice. Even when ice retreated, it left behind tundra-like conditions, barren soils, and a landscape slow to recover. Fossil pollen preserved in sediments shows long stretches when forests vanished, replaced by grasses and shrubs adapted to cold and dryness. For hominins adapted to warmer, more diverse environments, these regions would have been hostile, not havens. In Central Asia, the picture was no more forgiving. As the Middle Pleistocene transition unfolded, deserts expanded. The Gobi, already arid, became even harsher. Less deposits in northern China reveal cycles of windblown dust thicker than before, evidence of massive erosion and dryness. These were not landscapes rich in game or plant food. They were barriers, difficult to cross and difficult to live in. Even rivers, often lifelines in arid regions, were less predictable, swelling during brief interludes and vanishing during long cold phases. For groups attempting to move eastward, deserts acted as traps, draining energy and resources with little return. Yet we know hominins were present. In Spain, sites such as Atapuerca preserve fossils of Homo antecessor dating to roughly 800,000 years ago. In northern China, Stone tools mark the presence of hominins at sites like 𝐓𝐈𝐌𝐏𝐻𝐒 Basin. These finds show that groups did push into Eurasia, but the record is sparse, and often there are long gaps between occupation layers. This pattern suggests that Eurasia was not continuously occupied, but rather intermittently visited or briefly settled during warmer interglacials. When the climate turned cold again, populations shrank or disappeared, leaving behind only fragments of stone and bone. This stop-and-go pattern makes Eurasia look less like a refuge and more like a testing ground. Groups that entered had to contend with rapid swings between warmth and cold. During interglacials, forests spread, rivers flowed, and animals migrated in abundance. During glacials, those same forests disappeared, animals retreated or died out locally, and resources became scarce. Hominins had little margin for error. A generation might grow up in relative abundance, only to find themselves adults in a barren, freezing landscape. The archaeological gaps may reflect these oscillations, with human presence waxing and waning along with the climate. The physical challenges were immense. Clothing, if it existed at all, would have been rudimentary, leaving groups vulnerable to frost and snow. Shelters were likely simple, inadequate against the deep cold of Eurasian winters. Fire may have been known in some places, though evidence is fragmentary at this stage, and its control was not yet widespread. Without reliable warmth, northern latitudes were deadly. Migration southward may have offered temporary relief, but returning glaciers and deserts created bottlenecks. Populations were squeezed into ever smaller pockets where survival was possible. Eurasia also presented ecological unfamiliarity. African hominins evolved alongside specific animals and plants. Moving into new regions meant encountering unfamiliar prey, different predators, and different hazards. Large carnivores such as cave lions, saber-toothed cats, and giant hyenas roamed the open plains. Hunting strategies that worked in Africa may not have translated easily to Eurasian landscapes. Failures in adaptation could mean starvation. The difficulty of migration itself should not be underestimated. To move across Eurasia required crossing mountain ranges, arid basins, and river systems. Each presented barriers that isolated groups. Even if one band succeeded in reaching a new valley or plateau, others might fail and vanish along the way. These barriers also limited contact between groups, reducing the exchange of knowledge and technology. Innovation, if it arose, might die with its inventors, never spreading across the continent. Still, the presence of sites like Atapuerca shows that some succeeded, at least for a time. How did they manage it? One possibility is timing. Groups may have expanded during brief warm periods when forests returned and animals flourished, only to retreat or perish when the climate swung back. Another possibility is local refugia within Eurasia itself. Certain valleys, coastal areas, or river corridors may have remained habitable even during cold phases, sustaining small populations. But these refugia were not abundant, and their capacity was limited. The haunting implication is that Eurasia was both opportunity and graveyard. It drew hominins outward, promising resources during favourable times, but it punished them harshly when conditions shifted. This cycle of expansion and collapse may explain why the fossil and archaeological record is so sparse. Few groups persisted long enough to leave many traces. Those that did are rare exceptions, flickers of presence against a backdrop of absence. From today's perspective, we might be tempted to see Eurasia as a step toward global expansion, the first exploratory movements that would eventually lead to worldwide dispersal. But in this time frame, it was less a triumph than a struggle. Eurasia was not yet a land of conquest. It was a land of attrition where small populations tested the limits of endurance. Many failed, and only a few left fossils to remind us they were ever there. The haunting question remains: if Eurasia was so hostile, why venture there at all? The answer may lie in desperation. As Africa's climate turned harsher, some groups may have had little choice but to move. Pushed by drought, shrinking food sources and competition, they ventured outward into unknown lands. The choice was not between comfort in Africa and hardship in Eurasia. It was between hardship in both, with the faint hope that somewhere beyond the horizon lay better chances. That gamble kept the human lineage alive, but at a terrible cost. Did the survivors evolve into 𝐓𝐈𝐌𝐿𝐌𝐏𝐻𝐒, our last common ancestor? That possibility has intrigued paleoanthropologists for decades, and it has taken on new weight as genetic models reveal the scale of the bottleneck that nearly erased our lineage between 1 million and 700,000 years ago. The idea is simple but profound, that those few scattered groups who endured through droughts in Africa and cold in Eurasia may have been the seed population from which 𝐓𝐈𝐌𝐿𝐌𝐿 emerged, a species that many researchers consider the pivotal bridge linking earlier hominins, with both Neanderthals and modern humans. If true, it means that what we almost became, balanced on the edge of extinction, is precisely what shaped the later success of our genus. The reveal is rooted in timing. Fossils attributed to 𝐓𝐈𝐌𝐿𝐌𝐿𝐼, or to closely related archaic humans, begin appearing around 700,000 years ago. They show up in Africa and Europe, with specimens like those at 𝐓𝐈𝐌𝐿𝐌𝐿 in Zambia, Arago in France, and later Bodo in Ethiopia. These hominins had larger brains than earlier species, averaging over 1,000 cubic centimetres, and more robust bodies adapted to diverse environments. They made advanced Acheulean hand axes, hunted large game more effectively, and seemed to have spread widely across the Old World. Their rise coincides strikingly with the recovery from the bottleneck, when genetic diversity began to expand again. It is tempting, then, to draw a line between the small population that survived the Middle Pleistocene transition and the emergence of this influential species. 𝐓𝐈𝐿𝐌𝐿𝐼 occupies a controversial place in human evolution. Some scholars see it as a distinct species, the common ancestor of both Neanderthals in Europe and Homo sapiens in Africa. Others argue that it is more a convenient label for a cluster of transitional fossils that do not fit neatly into earlier or later categories. Regardless of the taxonomy, what matters is that around this period, a new kind of hominine appears, with features that foreshadow both us and our closest extinct relatives. That suggests that the survivors of the bottleneck did not simply endure unchanged, they evolved. How does a population evolve under such pressure? One possibility is that small, isolated groups experience stronger genetic drift, meaning that random changes in traits could spread more quickly than in large populations. Another is that the harsh environmental conditions selected for greater adaptability, larger brains, or more complex behaviours. Those groups that could innovate, cooperate, and adjust to shifting climates had a better chance of surviving and passing on their traits. Over thousands of generations, this gradual filtering could produce the more capable hominins we recognise in the fossil record as 𝐓𝐈𝐿𝐌𝐿𝐼. The fossils themselves tell part of the story. The 𝐓𝐈𝐌 skull, found in Zambia and dated to roughly 300,000 to 200,000 years ago, shows a mixture of traits: heavy brow ridges and robust features like earlier species, but a cranial capacity approaching that of modern humans. The Bodo cranium from Ethiopia, and about 600,000 years old, similarly combines archaic and modern traits. In Europe, the Arago fossils show parallels, hinting at populations adapting to colder climates while retaining connections to their African roots. These specimens may not represent a single uniform species, but together they suggest a population that had moved beyond Homo erectus, yet had not yet become Neanderthals or Homo sapiens. What is striking is how global this pattern becomes. Homo erectus had spread widely from Africa into Asia, but its morphology remained relatively conservative for nearly 1 million years. Around the time of the bottleneck and its aftermath, variation increases. Different populations begin to show new traits, larger brains, and more advanced technologies. It is as though the bottleneck did not just prune the tree of humanity, but reshaped its branches, leading to a new phase of diversification. The survivors may have carried forward traits that allowed for more rapid adaptation, setting the stage for later evolutionary leaps. Still, caution is warranted. The fossil record is incomplete, and the assignment of specimens to 𝐓𝐈𝐿𝐌𝐿𝐼 is debated. Some researchers prefer to use other names, such as Homo rhodesiensis for African fossils, or early Neanderthals for European ones. The precise taxonomy may never be resolved, but the pattern of transition is clear enough. Something changed in our lineage between 1 million and 700,000 years ago, and it coincided with the aftermath of a near extinction. What does this mean for us? If 𝐓𝐈𝐿𝐼 truly was our common ancestor, then our own existence is tied directly to the resilience of those small populations. Their ability to endure long droughts and cold phases gave rise not only to Neanderthals and Denisovans but to us. Had they failed, the story of humanity might have ended in silence, with no one left to ponder what could have been. Instead, they adapted, and in doing so they became the foundation for all later branches of our genus. There is a haunting irony in this. We often think of Homo sapiens as the pinnacle of a long evolutionary process, but that process was shaped not only by triumphs, but by failures, losses, and narrow escapes. Homo heidelbergensis may represent one of those narrow escapes turned into opportunity. From the perspective of deep time, the species was both a survivor and a bridge, not an endpoint but a transition. What we almost became is what allowed us to become what we are. The resolution here is not final. We cannot say with absolute certainty that Homo heidelbergensis was the direct ancestor of all later humans. The fossil record does not permit that level of precision. What we can say is that the survivors of the bottleneck evolved into new forms, and those forms bore the hallmarks of what would later define humanity. Larger brains, more sophisticated tools, and the ability to thrive in diverse environments. They were not yet us, but without them, there would be no us. The haunting question that lingers is whether our survival was inevitable or accidental. Did the bottleneck create the conditions that drove the evolution of Homo heidelbergensis, or would something similar have happened anyway? If the climate had remained stable, would humans have evolved along a gentler path? Or did the harshness of the Middle Pleistocene transition force the emergence of a lineage capable of greater adaptability? We do not know, but the silence of the fossils and the narrow thread of genetics suggest that the line we followed was fragile, and that what we almost became was only one of many possibilities. Who didn't make it out of the bottleneck alive? It is a question that reminds us that evolution is not a straight march forward, but a tangled bush of experiments, many of which ended abruptly. Between 1 million and 700,000 years ago, when the human lineage passed through its most severe population crash, some lineages survived and gave rise to future branches, but others vanished, leaving only fragments of bone and unanswered questions. These are the ghost species and empty branches, the hominins who may once have flourished in certain corners of the world, but whose lineages did not continue. Their stories are incomplete, but their presence in the fossil record is a reminder of how precarious survival can be. The reveal comes most clearly in the case of Homo antecessor, a species known primarily from fossils discovered at Atapuerca in northern Spain. These remains, dated to around 800,000 years ago, include partial skulls, jaws, and teeth. They suggest a hominin with a mixture of archaic and modern features, a projecting face more like Homo sapiens than earlier species, but also primitive traits in the jaw and brow. For a time, Homo antecessor was considered a strong candidate for the last common ancestor of later humans. But the genetic bottleneck and subsequent discoveries have complicated that picture. Today, many researchers see Homo antecessor as an evolutionary experiment, a branch that flourished briefly in Europe but did not contribute directly to the lineages that followed. The fate of Homo antecessor highlights the challenges of living in Eurasia during the Middle Pleistocene transition. The species appears to have adapted to European environments during a warmer interval, leaving tools and butchered animal bones that show it was capable of hunting and processing large prey. Yet the record is sparse, and after a few layers, it vanishes. No continuous sequence connects these fossils to later populations. The simplest explanation is extinction. As glacial cycles intensified, resources dwindled, and the fragile foothold Homo antecessor had established in Europe was lost. The species became another empty branch in the evolutionary bush. Homo antecessor is not the only ghost species of this period. In Asia, there are fossils that do not fit neatly into Homo erectus or later categories. At sites in China, such as 𝐓𝐿𝐌𝐿 and Dali, skulls show a mosaic of traits. Some have large cranial capacities approaching later humans, but robust features more reminiscent of earlier species. Taxonomic labels have varied, with some researchers suggesting distinct lineages and others preferring to fold them into broader categories. The uncertainty reflects both the fragmentary nature of the fossils and the possibility that many of these lineages did not survive. They may represent regional populations that evolved locally, but eventually disappeared, leaving no descendants. Africa too may have hosted ghost species during this time. Fossils from sites such as Buya in Eritrea and 𝐓𝐈𝐌𝐿𝐄𝐒 in Kenya hint at diversity, though the evidence is limited. The Buya skull, dated to around 1 million years ago, combines features of Homo erectus with more advanced traits. Was it part of a population that contributed to later lineages, or was it another branch that vanished in the bottleneck? We cannot be certain. The thinness of the fossil record during this period means that many lineages may have risen and fallen without leaving enough evidence to reconstruct their stories. The concept of ghost species is not just speculative. Genetic evidence from later periods shows that extinct hominins interbred with surviving ones, leaving traces of their DNA in our genomes. This tells us that hominin diversity was often greater than the fossil record suggests. During the bottleneck, many of these diverse populations likely disappeared, their genetic legacy erased. The lineages we know, and the few fossils we can hold in museums, are survivors of a much broader experiment. Evolutionary pruning is a useful metaphor. Imagine a tree with many branches. At certain times, branches flourish, growing leaves and spreading outward. At other times, drought or frost cuts them back, leaving only a few survivors. The bottleneck around 900,000 years ago was such a frost. Many branches were cut short. Only a narrow trunk continued upward, carrying with it the potential for later diversification. Homo antecessor and others represent the branches that never made it past that pruning. The haunting part of this realization is how contingent survival is. Homo antecessor may have seemed, at its time, as viable a species as any. Its tools and hunting abilities suggest competence. Its facial structure hints at evolutionary promise. Yet competence was not enough in a world where climate swung violently and resources vanished for centuries. The difference between survival and extinction may have been luck as much as adaptation. A few groups happened to occupy refugia that remained habitable, while others did not. The ghost species are reminders that being human-like was no guarantee of becoming human. When we look at these fossils today, the temptation is to fit them into a neat lineage, to ask whether Homo antecessor was really our ancestor or not. But evolution does not work in neat lines. It is messy, with populations splitting, merging, and vanishing. Some contributed genes to future species, others left no trace. The absence of continuity in the record for Homo antecessor and similar fossils suggests they belong to lineages that were pruned away. But we cannot exclude the possibility that they contributed in ways we cannot yet detect. Perhaps some of their traits lived on indirectly, folded into other populations before they disappeared. The silence of genetics before 400,000 years ago leaves such questions open. Still, the larger point is clear. The bottleneck was not only a reduction in numbers, it was a winnowing of diversity. Multiple lineages existed before, but only a few survived after. The human family tree, which had once been bushy, became narrower. The ghosts remind us of what was lost, faces that looked familiar, but whose stories ended long before ours began. The resolution we can take from this is not certainty but humility. We know some species vanished, we know others endured, we do not know exactly why. The haunting question that remains is whether those lost lineages were truly doomed by circumstance, or whether in another roll of the evolutionary dice they might have been the ones to carry the story forward. If Homo antecessor had survived, would the human story look different today? Would we be descended from Europeans rather than Africans? Would we even recognize ourselves in such an alternate lineage? We cannot know. What we can say is that extinction is the rule, survival the exception, and the ghosts of our past are as important as the ancestors who succeeded. Why do we have 23 pairs of chromosomes when chimpanzees, gorillas, and orangutans all have 24? It is a detail that high school biology textbooks often mention in passing, but behind it lies one of the most consequential quirks in our evolutionary story. Somewhere in the deep past, 2 chromosomes fused end to end, creating what we now call chromosome 2. This event permanently altered the genetic blueprint of the lineage that led to us. And intriguingly, genetic analyses suggest that this merger took place around 900,000 years ago, within the same time frame as the population bottleneck that nearly erased our ancestors. Whether coincidence or not, the merger stuck, passing through the narrow filter of survival and defining every human alive today. The reveal of this fusion came relatively recently in science. When researchers sequenced the human genome and compared it to that of other great apes, the difference in chromosome count was obvious. Apes have 24 pairs, we have one less. The missing pair was not lost. Instead, two ancestral chromosomes had joined together, their tips fused, and redundant sequences silenced. At the point of fusion in human chromosome 2, scientists found telltale remnants, vestiges of telomeres, the repetitive caps normally found at the ends of chromosomes, now stranded in the middle, and two centromeres where only one is needed, one of them inactivated. These molecular scars are the fingerprints of an ancient union. The timing is harder to pin down, but genetic models suggest that the fusion was already fixed in the population by about 900,000 years ago. That means every surviving individual carried it, and it had become a permanent feature of the lineage. Before that point, it may have arisen in a single individual as a rare mutation. Carried by that individual's children, it could have spread slowly, generation by generation. Normally, such a fusion might have disappeared again, lost by chance. But during the bottleneck, when populations were small and lineages fragile, the odds of such a mutation becoming universal increased. Once the survivors all shared it, there was no going back. The implications of this fusion are still debated. At a simple level, it reduced the chromosome count from 24 pairs to 23. That alone did not necessarily change the function of genes, since the DNA content remained the same. But chromosome architecture can affect how genes are regulated, turned on and off, and recombined. By joining two chromosomes into one, the merger may have reshuffled regulatory regions, changing how certain genes were expressed. We do not yet know which traits, if any, were directly influenced by this event. What we do know is that it marked a permanent divergence from our closest relatives. No living ape has this fusion. Every human does. There is an important caveat. Not all scientists agree on the precise date. Some argue that the fusion could have happened earlier, perhaps over 1 million years ago, and only became fixed later. Others suggest that genetic clocks, while powerful, may not resolve the timing finely enough to tie the event closely to the bottleneck. But the broad consensus is that the fusion was established around the period when human ancestors were passing through one of their hardest evolutionary trials. This overlap tempts us to imagine a connection, that the fusion was part of what defined the survivors. We cannot prove this, but the coincidence is striking. To understand why such a fusion would persist, it helps to think about how chromosomal differences affect reproduction. In many animals, mismatched chromosome numbers between parents can lead to fertility problems. If one lineage of apes with 24 pairs interbred with another that had the fused chromosome, their offspring might have had difficulties in meiosis, the process of forming sperm and eggs. But if the fused chromosome carried no serious disadvantages, and if the population was small enough, the mutation could spread until it replaced the older arrangement entirely. Once everyone in the group carried the same fusion, reproductive compatibility was restored. The merger became the new normal. This raises a deeper question. Could the fusion have helped isolate our ancestors reproductively from other hominins? If groups with the fusion became less compatible with groups without it, even slightly, then gene flow between them would have been reduced. Over time, this reproductive barrier could have reinforced divergence, helping to define a new lineage distinct from others. In this sense, the fusion may not only have been a quirk of chromosomes, but a step towards speciation. Again, we cannot prove this, but it is a plausible scenario, and it underscores how structural mutations can shape the trajectory of evolution. When we look at chromosome 2 today, we are seeing more than just a string of DNA. It is the second largest chromosome in the human genome, carrying about 8% of our genetic material. Within it are hundreds of genes involved in diverse functions. That such a large structure was created by a fusion event is remarkable. Most chromosomal mutations are harmful, causing genetic disorders or infertility. This one not only avoided catastrophe but endured, shaping the genome of billions of people today. There is something humbling about realizing that every cell in our bodies carries the mark of this ancient event. The molecular scars of the fusion are still there, detectable under a microscope. Each time our cells divide, they replicate this fused chromosome, passing it on faithfully. It is a reminder that deep evolutionary history is not an abstract story, but a living part of us, written into the structure of our DNA. We must also recognize what we do not know. Did this fusion directly influence traits that helped our ancestors survive the bottleneck? Or was it simply carried through by chance, its fate tied to the survival of a tiny population? At present, science cannot answer. The fusion might have been neutral, neither helping nor hindering, merely surviving because the people who carried it survived. Or it might have subtly altered gene regulation in ways that mattered for endurance in harsh climates. Both possibilities remain open. Either way, the fact that the fusion became universal at this critical juncture emphasizes the role of contingency in evolution. A single event, in a single cell, in a single individual, 900,000 years ago, may have altered the trajectory of our species. Had that individual died young, or had their lineage been among the many that vanished, chromosome 2 would not exist. Humans might still have 24 pairs of chromosomes like other apes. We might still be here, but we would be genetically different in ways we can barely imagine. The merger that stuck is a reminder that the survival of our lineage depended on countless fragile threads, any one of which could have snapped. The haunting question is how many other such quirks arose and vanished during the bottleneck. Chromosome 2 happened to survive. What about other mutations, traits or possibilities that were lost with the groups that did not endure? Our genetic legacy is not only what survived, but what was pruned away. Chromosome 2 is a survivor's tale, but behind it lies a shadow library of changes we will never know. Did intelligence save us when numbers could not? Between 900,000 and 800,000 years ago, our ancestors were a species reduced to fragments. The global population, as far as genetic reconstruction suggests, had been whittled down to barely more than 1,000 breeding individuals, scattered across landscapes that alternated between drought and ice. Numbers this low should have meant extinction, yet they did not vanish. One hypothesis is that survival in this crisis depended less on physical robustness and more on cognitive flexibility, the ability to think, to adapt, and to find creative solutions in environments that change faster than bodies could evolve. The reveal here is subtle. Fossils from this period show that brain size, which had already been expanding in earlier hominins, began to reach new levels. By 800,000 years ago, average cranial capacity had grown larger than that of Homo erectus and approached that of later archaic humans. The Bottlecranium in Ethiopia, dated to roughly 600,000 years ago, demonstrates this increase clearly, though it comes after the deepest part of the bottleneck. Other specimens, fragmentary as they are, hint at a trajectory of enlargement already underway during the crisis. Brain growth does not prove intelligence in the modern sense, but it suggests that our ancestors had begun to develop the neural capacity for more complex behaviours. What kinds of behaviours might have mattered most? Archaeological evidence points to gradual refinements in stone tool technologies. The Achillean hand axe tradition, which had already begun over 1 million years earlier, became more standardized and symmetrical during this time. Tools were crafted with greater care, suggesting not only motor skill but planning and teaching. A more finely made tool could butcher an animal more efficiently, or split wood more effectively. Small advantages that could mean survival when resources were scarce. Even subtle improvements in technique would have magnified across generations, allowing small groups to extract more from their environments than before. Cognition may also have helped in mobility. During the Middle Pleistocene transition, landscapes shifted repeatedly between fertile and barren. Groups that could recognize patterns, remember routes, and anticipate seasonal changes would have been better positioned to move between refugia. Navigation is a cognitive skill, requiring memory, spatial awareness, and social communication. A band that could recall the location of a distant spring or follow the migrations of animals would have outlasted one that relied only on instinct. In this sense, intelligence was not abstract but a practical tool, as vital as stone or bone. Social intelligence is another likely factor. In small, endangered populations, cooperation is essential. Sharing food, protecting vulnerable members, and coordinating hunts all require communication and trust. Fossil evidence of group living is indirect, but the clustering of tools and bones at certain sites implies cooperative activity. Cognitive shifts that supported empathy, Planning, or rudimentary symbolic thought may have strengthened social bonds, making groups more resilient. A lone individual could not have survived a megadrought or glacial advance. A cohesive band, however, could pool resources and knowledge. Intelligence, in this context, was not simply about individual cleverness, but about group survival. It is tempting to imagine these early humans sitting at the edge of drying lakes, puzzling out new ways to crack bones or trap animals. Of course, we cannot know the details of their thoughts, but we can infer that whatever mental capacities they possessed were sufficient to carry them through conditions that nearly erased them. If numbers alone had determined their fate, they would have vanished. Something else tipped the balance, and cognition is one of the most plausible candidates. The debate among scientists is ongoing. Did the increase in brain size precede the bottleneck, and thus simply happen to be present in the survivors? Or did the prolonged stress of the bottleneck itself accelerate selection for larger, more capable brains? The genetic record cannot answer this, and the fossil record is too sparse to be definitive. Yet the correlation is suggestive. By the time populations began to recover, brains were bigger, tools were more refined, and behaviours were more flexible. The crisis may have been both a threat and a crucible. Still, humility is required. We cannot say with confidence that intelligence alone explains survival. Other factors, ecological luck, access to refugia, sheer chance, surely played roles. It is possible that intelligence was necessary but not sufficient, a background trait that increased the odds without guaranteeing success. After all, other hominins with respectable brain sizes, such as Homo antecessor, did not persist. What intelligence offered was not immunity to extinction, but a slightly better hand in a rigged game. That hand, played over 100,000 years, proved enough. The haunting aspect of this idea is that intelligence may have emerged not as a gift, but as a response to desperation. The harshest environment selected for the cleverest problem solvers. Creativity, memory, and planning were not luxuries but survival mechanisms. Our lineage may carry its remarkable mental abilities, not because the universe favoured brilliance, but because failure to innovate meant death. The very faculties we now use to build cities and write books may have their roots in the quiet struggle of small bands trying to keep children alive through drought and cold. And so the question lingers, if not for the bottleneck, would intelligence have advanced as it did? Perhaps without the prolonged crisis, evolution would have favoured physical adaptations instead. Thicker fur, stronger jaws, or faster legs. Instead, the environment rewarded brains. We are the descendants of that reward, carrying in our heads the legacy of 100,000 years when thinking was survival. What if the cold hit before we controlled fire? Between 900,000 and 700,000 years ago, the world was growing harsher. Ice sheets advanced further south in Eurasia. Africa endured prolonged droughts, and the human lineage itself dwindled to a shadow of its former numbers. In such an environment, fire would have been an unmatched ally. It could provide warmth against freezing winds, safety from predators, and a means of cooking food to unlock more calories. Yet the archaeological record of this period offers almost no firm evidence of fire use. For those who struggled through the bottleneck, it seems they did so largely without flame. The reveal is in the silence. Archaeologists search for fire in the form of hearths, ash deposits, and burnt bones. In younger sites, these traces appear often enough to suggest regular use. In older sites, particularly before 700,000 years ago, they are scarce. There are a handful of disputed hints: patches of reddened soil, stones cracked by heat, bits of charred material, but none that most researchers accept as unambiguous. The absence is striking. If humans of this period had mastered fire, we would expect clearer repeated evidence across multiple sites. Instead, what we see is a long gap, a shadow in which survival seems to have been achieved without this powerful technology. The implications are sobering. Without fire, hominins were at the mercy of their environments. In Africa, cold was less of a problem, but droughts left nights bitter in highland regions and forced reliance on raw plant foods and uncooked meat. In Eurasia, the absence of fire was even more dire. Winters would have been brutal, with snow and freezing winds. A band without fire could not easily remain in northern latitudes during glacial phases. This may help explain the intermittent presence of hominins in Eurasia during this time. They could venture northward during warm interglacials, but were forced back or extinguished locally when the climate turned cold again. Fire might have allowed permanent settlement. Without it, survival was seasonal, precarious, and marginal. Cooking, too, would have been transformative had it been available. Raw meat is difficult to digest. Raw tubers are often toxic or indigestible. Fire transforms both, making calories more accessible and expanding the range of edible foods. Without cooking, diets would have been constrained, especially when easy foods were scarce. During droughts or in cold steppes, the ability to process otherwise inedible plants, or to preserve food by drying over flames, might have made the difference between starvation and survival. The lack of such options meant our ancestors lived closer to the nutritional edge. Some researchers argue that the very scarcity of fire evidence is itself revealing. Perhaps early humans could sometimes capture fire from natural sources, lightning strikes, wildfires, or smouldering trees, but they could not make or maintain it reliably. If so, fire use was opportunistic, not controlled. A group might have enjoyed warmth and cooking for a few days or weeks, only to lose it when the flames died. In such a scenario, fire was a fleeting advantage, not a dependable technology. It would explain why traces are so rare in the record. Moments of fire use were exceptional, not routine. The absence of fire also shaped social life. Later, hearths would become gathering places, centres of community and teaching. In this earlier period, nights would have been darker, colder, and more dangerous. People may have huddled together for warmth, but they lacked the light to extend social activity into the evening. Knowledge sharing, tool making, and storytelling, activities often imagined around a fire, would have been limited to daylight hours. Darkness curtailed culture. Fire was not yet a medium of social expansion. Still, we must be careful not to impose too much modern imagination on the past. The fact that fire is not clearly present does not mean our ancestors were helpless. They adapted with what they had. They may have used shelters of wood or stone to block wind, or animal hides for insulation. They may have relied on body heat and group sleeping for warmth. For food, they may have chewed fibrous plants longer, cracked bones for marrow, or eaten meat raw despite the risks. These were not ideal strategies, but they were sufficient, at least sufficient to keep the lineage alive, however tenuously. The haunting part of this story is the thought of how different survival might have been if fire had arrived sooner. Imagine the bottleneck not without flame but with it. Would the population have remained so low for so long? Would hominins have been able to spread more widely, leaving behind more fossils and tools? Would the bottleneck have been less severe, or avoided altogether? We cannot know. What we can say is that the near absence of fire evidence during this period suggests that one of humanity's greatest allies was not yet in play. Our ancestors faced the cold and the dark with nothing but stone, bone, and each other. And that leads to the lingering question, why not fire? Other animals, such as birds of prey, have been observed using wildfires to hunt, driving prey from the flames. Humans would certainly have seen natural fires and their potential. Yet control is another matter. Striking sparks, carrying embers, keeping fires alive overnight. These are not trivial skills. They require experimentation, practice, and cultural transmission. Perhaps groups experimented and failed, or perhaps the knowledge arose but was lost repeatedly in the fragility of tiny populations. Fire, like language or culture, depends not only on discovery but on continuity. During the bottleneck, continuity was in short supply. The resolution here is that the absence of fire did not doom our ancestors, but it limited them. They endured without it, proving resilience in its absence, but they did so at great cost. Later, when fire use became reliable, the human story accelerated. In this earlier era, it was the fire that wasn't there, a missing tool that could have eased suffering but did not. The haunting question is whether the bottleneck itself might have been shorter or less severe if fire had arrived earlier. Would there have been more of us sooner? Or did the absence of fire forge a lineage that learned to endure without it, shaping resilience in other ways? The silence of the archaeological record gives no final answer. Only the dark image of hominins staring into nights without flame, surviving one cold at a time. Did seas suffocate too? When we speak of the Middle Pleistocene transition, we often picture ice sheets across northern continents and dry savannas in Africa. But the story was not only written on land. The oceans, vast and seemingly stable, also shifted dramatically during this period. Marine sediments reveal changes in oxygen levels, reorganizations of circulation, and losses of species. While our ancestors struggled with droughts and cold, the seas themselves were undergoing a crisis, one that would have reshaped the food webs of fish, sharks, and dolphins. The reveal comes from geochemistry. Deep-sea cores extracted from the Atlantic, Pacific, and Indian Oceans preserve chemical fingerprints of past oxygen levels. Tiny shells of foraminifera, when analysed for isotopic composition, tell us not only about global ice volume, but also about the conditions of the water in which they lived. During the Middle Pleistocene transition, the signals shift. Evidence points to intervals of reduced oxygen in the oceans, what scientists call oceanic anoxic events on smaller scales. While not as catastrophic as some events in deep geological history, such as those of the Cretaceous, these Pleistocene episodes were still severe enough to leave a mark. Zones of low oxygen expanded, stressing marine life and altering ecosystems. The causes are tied to the very same climate mechanisms that restructured the land. As ice sheets grew larger and glacial cycles lengthened from 41,000 to 100,000 years, sea level dropped by tens of meters. Continental shelves were exposed, altering habitats for countless species. Ocean circulation, driven by differences in temperature and salinity, changed as ice sheets poured fresh water into the seas and as winds shifted across continents. These disruptions slowed the renewal of oxygen in deep waters. Where circulation faltered, oxygen declined, creating suffocating zones hostile to most large animals. The consequences ripple through the fossil record. Some species of fish vanish from the layers corresponding to this interval, replaced by new assemblages better adapted to low oxygen conditions. Sharks, which had long thrived as apex predators, show declines in diversity. Fossil teeth, which are abundant and resistant to decay, drop in frequency for certain lineages. It is not that sharks disappeared entirely there, they remain to this day, but particular groups seem to have dwindled or vanished, unable to adapt to changing prey availability and shifting ocean conditions. Marine mammals were not spared. Dolphins and small whales, adapted to productive coastal ecosystems, faced losses when food chains collapsed. If fish populations declined due to low oxygen, predators dependent on them would have suffered. Fossil evidence suggests that several lineages of early dolphins and small-toothed whales did not persist beyond this period. The oceans did not empty, but they thinned, pruning diversity in ways parallel to what was happening on land. For plankton, the foundation of the marine food web, the transition was equally disruptive. Shifts in species composition are visible in microfossils. Some groups declined, while others expanded, reflecting changes in nutrient availability and circulation. These tiny organisms are not as charismatic as sharks or dolphins, but their fates controlled the productivity of the entire ocean. A change in plankton cascades upward. Fewer plankton means fewer small fish. Fewer small fish means fewer large fish, and eventually fewer dolphins or sharks. The haunting part is how invisible these changes would have been to our ancestors. Standing on a shoreline, they might have noticed fewer shellfish, fewer fish in shallows, or changes in the behaviour of seabirds. But the global reorganisation of marine oxygen, currents, and biodiversity would have been beyond their comprehension, yet it mattered to them, indirectly. If coastal zones became less productive, humans had fewer resources to exploit when they reached them. Migration routes that might once have offered food from rivers or deltas may have been barren during these intervals, compounding the challenges of survival. The science of reconstructing these events is still developing. Oxygen levels in the oceans are difficult to estimate for periods nearly 1 million years ago. Researchers rely on proxies, the isotopic composition of carbon and nitrogen in sediments, the presence or absence of certain microfossils, the layering of organic-rich shales. None are perfect, and debates continue about the exact scale of oxygen loss during the Middle Pleistocene transition. But the broad agreement is that marine ecosystems changed substantially, with extinctions and reorganizations that parallel the crises on land. This brings us to the haunting question of contingency. The oceans are Earth's lungs, producing much of the oxygen we breathe and absorbing carbon dioxide that shapes global climate. If marine ecosystems had collapsed further, would our ancestors have had any chance at all? It is possible that the bottleneck on land was partly linked to stresses in the sea, even if indirectly. Changes in atmospheric carbon dioxide tied to ocean circulation may have amplified the glacial cycles that made Africa drier and Eurasia colder. In this way, suffocating seas may have contributed to suffocating landscapes. The crises of ocean and land were not separate but entangled. And yet, life endured. Sharks did not vanish completely. Dolphins diversified again in later epochs. Fish recovered as climate stabilized into the new rhythm of 100,000-year cycles. The oceans breathed again, though differently than before. Just as on land, extinction was not total. It was selective, pruning some lineages and sparing others. The survivors inherited a changed world. The resolution is a reminder that stability is rare in Earth's history. Even the oceans, vast and ancient, are not immune to disruption. Their rhythms are tied to the ice on continents, the winds in the sky, and the tilt of the planet itself. To live through the Middle Pleistocene transition was to endure not just droughts and ice, but seas running out of breath. Our ancestors may not have seen it directly, but they lived in its shadow, their fate bound to the unseen transformations of the waters that cover most of the planet. The haunting question remains, are we too at the mercy of the ocean's breath? As modern climates warm and oxygen levels in the seas decline again, the echoes of the Middle Pleistocene remind us how fragile marine systems can be. For our ancestors, the suffocation of the seas was another filter on their survival. For us, it may be a warning. What Ice Age beasts never returned? When we picture the Pleistocene, we often imagine vast herds of mammoths, bison, and giant deer, with saber-toothed cats stalking the grasslands. But between 1 million and 700,000 years ago, as the Middle Pleistocene transition reshaped Earth's climate and ecosystems, many of the great terrestrial animals did not survive. The bottleneck that nearly erased our own ancestors was not unique to humans. It was part of a wider pruning that swept across the land, removing predators and prey alike, leaving empty spaces in ecosystems that would be filled by different species later. Some of these losses are obscure, remembered only through fragmentary fossils, yet they are reminders that survival was not guaranteed even for the strongest jaws and sharpest claws. The reveal comes from predators, always the most vulnerable in times of scarcity. One of the most striking disappearances was Meganodon, a saber-toothed cat that had roamed Eurasia. With massive canines designed to pierce the hides of large herbivores, it was a formidable hunter in more stable times. But as climates shifted, prey populations dwindled. Forests gave way to more open habitats, then to cold steppes. The specialized hunting strategies of saber-toothed cats, perfected for ambush in denser cover, became less effective. Their large size and high energy demands left little room for flexibility. By the middle stages of the transition, Meganodon was gone, a victim of ecological change that cut down not only prey, but also the predators who depended on them. Canids suffered too. The genus Xenos, an ancient branch of the dog family, nearly disappeared during this period. These were not wolves as we know them, but earlier canids that had once been diverse across Eurasia and North America. Their fossils suggest medium-sized hunters and scavengers, capable of cooperative behaviour. Yet the record shows a sharp decline around the time of the bottleneck. Climate stress likely reduced prey availability, while competition from both big cats and more adaptable wolves intensified. By the end of the transition, Xenos was reduced to a shadow of its former diversity, and eventually it vanished altogether, leaving no direct descendants. Even among felines, losses were not confined to the saber-tooths. Fossils suggest that several species of early pumas and other small cats disappeared. These animals had thrived in environments with abundant prey, but when ecosystems collapsed, their niches were erased. The cats we know today, lions, leopards, cheetahs, would later evolve or expand to fill open spaces. But in the middle of the Pleistocene, extinctions left gaps that were not immediately filled. It was a pause in the continuity of carnivore evolution, a reminder that predators are the first to fall when food chains falter. Herbivores also faced losses, though the evidence is less dramatic. Many large grazing animals shifted ranges or declined, fragmenting populations. Some species of ancient antelope, deer and horses disappeared from fossil records in regions where they had once been abundant. These losses compounded the struggles of predators. Without stable prey, carnivores were left with too few options. An entire web of interdependence frayed, with threads snapping in multiple places. The haunting part of this picture is that extinction was not selective in the way we often imagine. Strength, size, or ferocity offered no guarantee. Meganodon, with its fearsome teeth, was no more resilient than a delicate herbivore. Xenos, adapted for cooperative hunting, could not survive a shifting prey base. Ancient pumas, agile and resourceful, succumbed alongside them. The forces at play were larger than any single adaptation. Climate change did not reward strength, it rewarded flexibility, and even that was not always enough. These extinctions left legacies that echo into later ages. The disappearance of saber-toothed cats altered predator-prey dynamics. Without them, other carnivores such as early wolves and hyenas expanded into niches once filled by saber-tooths. The loss of canids like Xenos narrowed the evolutionary options for the dog family, leaving only certain lineages to diversify later. Each extinction was not just the end of a species, but the redirection of future possibilities. The ecosystems that followed were shaped by absences as much as by survivors. What is striking is how these losses parallel the human bottleneck. Just as our ancestors dwindled to a small remnant, so too did many of the animals around them. The crisis was not confined to one lineage. It was a broad ecological pruning, in which both hunters and hunted were cut back. Humans were not unique in their vulnerability. They were part of a larger pattern. The difference is that humans endured, while Meganodon, Xenos and ancient pumas did not. We must acknowledge uncertainty. Fossil records are incomplete, and it is possible that some of these species survived longer in isolated refugia, unnoticed by the geological record. But the overall pattern is clear enough. Diversity contracted. Whole lineages vanish from the fossil record around this time. The absences are too consistent across regions to be chance. Extinction was real, widespread and lasting. The resolution is bittersweet. The land animals that did not survive remind us of the fragility of even the mightiest forms. They remind us that extinction is not only a story of the far distant dinosaurs, but a constant feature of Earth's history, shaping who remains and who does not. For humans, the haunting question is simple. What made us different? Why did our small groups endure when so many other lineages, strong predators, successful hunters, resilient grazers, fell away? Was it chance, or was it some hidden flexibility we carried even then? We do not know. What we do know is that the landscapes our ancestors walked were emptier than before, stripped of predators and prey that had once ruled them. Every survival was shadowed by absence, every step taken in ecosystems marked by ghosts. Did huts save us when caves weren't enough? Around 700,000 years ago, the world was colder and harsher than it had been before. Ice sheets crept further south, deserts spread wider, and the climate swung between extremes with an unforgiving rhythm. Caves, long imagined as the natural refuges of early humans, were not always available. Many landscapes lacked them, and even where they existed, caves could be damp, smoky, or exposed. To survive in open plains or river valleys, our ancestors needed to improvise. Archaeology suggests that some of the earliest human-built shelters date to this period. Fragile constructions of wood, stone, and soil that may have given small groups a crucial edge in endurance. The reveal comes from a site in the Czech Republic at Pleistocene, where a circular foundation of stones has been interpreted as the base of a hut dating to roughly 700,000 years ago. The stones seem to have been deliberately arranged to anchor a structure, likely branches or poles bent into an arched roof, then covered with vegetation or hides. Though only traces remain, the pattern resembles later huts and lean-tos documented ethnographically. If correct, this would represent one of the first known examples of a purpose-built dwelling, distinct from natural shelters. It suggests that by this time, humans had begun to shape their environments more deliberately, not just occupy what nature offered. Other hints appear elsewhere. In parts of Africa and Eurasia, Circular or oval arrangements of stones or post holes in ancient sediments have been interpreted as foundations of temporary shelters. None are as clear as the Czech example, and debates remain fierce. Archaeologists must be cautious. Stones can be moved by rivers, and holes can be formed by roots. But the possibility of huts during this period aligns with a broader pattern of human adaptation under stress. Small, simple shelters could have made the difference between surviving a cold snap and perishing in the open. What did these shelters look like? Based on the evidence and analogies with later hunter-gatherer groups, they were likely small, perhaps large enough for a family or two. A circular ring of stones could have held down poles or branches, creating a dome-shaped frame. This might have been covered with leaves, grass, hides, or mud. Such a structure would not last long, weeks or months at most, but it could block wind, retain heat, and provide protection from rain or snow. Building one would have required planning, cooperation, and knowledge of local materials. It was not architecture as we think of it today, but it was engineering in its earliest form. The significance of these huts lies not only in physical comfort, but in what they reveal about cognition and society. Constructing a shelter requires forethought. One must collect materials, envision a design, and work together to assemble it. This suggests that groups of 700,000 years ago were capable of more complex planning than often assumed. They were not simply reacting to immediate conditions, but shaping their world to buffer against them. This marks a shift in the relationship between humans and environment, from passive occupants to active modifiers. Shelters also changed social life. A hut provided privacy and continuity. Families could sleep together under a roof they had built, protected from wind and predators. Even if crude, the structure defined a space, a boundary between inside and outside. Anthropologists have long noted how architecture creates social meaning. While we cannot know what meanings these early huts carried, it is reasonable to think that they were more than just piles of sticks. They embodied the effort and cooperation of those who built them, becoming symbols of community as well as survival. Of course, there are limits to what we know. Some archaeologists remain skeptical that the Pleistocene stones really represent a hut foundation. Natural processes could mimic deliberate patterns. The absence of clear roofing materials leaves room for doubt. Yet the possibility is supported by the broader context. Around this time, humans were experimenting more with environments, producing refined tools and adapting to a wider range of habitats. Building shelters fits that trajectory. Even if the evidence is sparse, it is consistent with what we might expect from populations enduring prolonged environmental stress. The haunting aspect of these fragile shelters is how little survives. Unlike stone tools, huts rot and vanish. Only the faintest traces, a circle of stones, a change in soil colour, remain after hundreds of thousands of years. For every hut we think we glimpse in the record, countless others are lost. The archaeological silence is not proof of absence, but of the difficulty of preservation. Yet, if even a few hints remain after so long, it suggests that building shelters may have been more common than we can document. Our ancestors may have been sleeping in huts, long before the oldest traces we can see. The resolution here is modest but profound. These early shelters were not grand constructions. They were small, temporary and crude, but they represent a leap in human ingenuity. By bending branches into roofs and anchoring them with stones, our ancestors demonstrated that survival was not only about enduring, but about inventing. When caves were not enough, they made their own. The haunting question is whether huts like these tipped the balance in the bottleneck. Did they provide just enough warmth, just enough safety, to keep small groups alive when others perished? We cannot know for sure, but the image of a few families huddled under a dome of branches in the cold wind of the Pleistocene is a reminder that even the simplest shelters can be acts of extraordinary resilience. If numbers collapsed, did technology collapse too? Between 900,000 and 800,000 years ago, our ancestors endured the long shadow of the bottleneck. Populations fell to a fraction of what they once were, scattered in fragile refuges, surviving against droughts, advancing ice, and predators that vanished almost as often as they endured. In such conditions, cultural transmission itself may have weakened. Stone tools, the durable signatures of early ingenuity, becomes scarce in the record. Archaeologists describe this interval as one of silence, a kind of technological dark age when invention faltered and survival left little time for refinement. The decline in tool industries parallels the decline in bones and campsites, suggesting that culture itself, as much as bodies, was under strain. The reveal begins with the Acheulean hand axe tradition. Before the bottleneck, Homo erectus and other early humans had spread across Africa and Eurasia, carrying with them bifacial stone tools shaped with care into symmetrical teardrops. These hand axes represented a step forward from the earlier Oldowan flakes, requiring greater skill, planning and teaching. They appear widely in sites older than 1 million years, yet as the Middle Pleistocene transition deepened, evidence of hand axes thins. Sites that once yielded abundant tools now go quiet. In regions where population shrank or vanished, the traces of stone industries vanish with them. Was this a collapse in knowledge, or merely in preservation? Archaeologists wrestle with this question. It is possible that the scarcity of sites reflects low population numbers rather than loss of skill. If only a few hundred or a few thousand individuals remained across continents, the odds of their camps surviving in the geological record would be slim. Fewer people meant fewer tools left behind and fewer sites to be buried and fossilized. Yet there is also evidence of stagnation, the same forms of tools repeated with little variation, suggesting that innovation slowed. Cultural continuity may have been fragile, with knowledge lost when small groups died or dispersed. In such a world, even something as basic as how to shape a hand axe might vanish with a single band. At sites like Boxgrove in England and 𝐓𝐈𝐌𝐿𝐿 in Kenya, hand axes appear in later layers, showing that the tradition persisted. But between 900,000 and 800,000 years ago, gaps in the record are telling. Acheulean technology was never universal, and in some regions toolkits reverted to simpler forms. Flakes and cores, the older and cruder tools of earlier hominins, dominate some assemblages. Whether this was adaptation to local resources or evidence of cultural regression is debated. Either way, the diversity of tool industries narrowed. It was as if the global crisis had trimmed not only populations, but also the range of cultural strategies available. The haunting implication is that technology, like genes, passed through its own bottleneck. Just as genetic diversity was reduced by the near extinction of our ancestors, so too cultural diversity may have been pruned. Innovations that might have existed before, new flaking techniques, experimental forms, could have been lost forever when the groups who carried them vanished. Archaeology cannot show us what was lost, only what remained. But the long stretches of silence in the record hint at cultural extinctions that paralleled biological ones. Still, we must be cautious. Absence of evidence is not evidence of absence. The record is patchy, and erosion, burial and chance all determine what survives. Some archaeologists argue that what we call a dark age may be an illusion of preservation. Perhaps humans were still making and using tools as before, but their camps were in regions where sediments did not preserve them. This is possible, but even if so, the scarcity still reflects fragility. Whether tools were absent or simply invisible, the result is the same. The record of this era is thin, and cultural continuity was precarious. The context of this stagnation is critical. Populations were small, resources were scarce, and environments were unstable. In such conditions, cultural innovation requires stability and time. Luxuries these groups did not have. A small band focused on finding water and food has little capacity for experimentation. Teaching children the basics of survival may have taken precedence over refining stone knapping techniques. In this sense, the bottleneck was not just a crisis of numbers, but a crisis of culture. It reduced not only the body of the species, but the collective memory of its skills. Yet resilience persisted. Even in this apparent dark age, some groups continued to make Acheulean hand axes, keeping alive a tradition that had spread across continents. This continuity suggests that while innovation slowed, the core of technological knowledge endured. The survivors may not have invented much that was new, but they maintained enough to survive. The Acheulean toolkit, simple by later standards, was versatile enough to cut meat, work wood, and prepare hides. It may have been the minimum needed to persist through the bottleneck, carried by memory from one generation to the next, even as populations collapsed around them. The haunting question is what we lost. Did some groups discover techniques beyond the 𝐓𝐈𝐌𝐿𝐼𝐴n, finer flaking methods, composite tools, or uses of materials we cannot detect? If so, those experiments may have died with the people who carried them, erased from history by extinction. The dark age of tools is not only about what we see, but about what we cannot. The silence in the stones may be an echo of vanished cultures as much as vanished populations. The resolution is paradoxical. On the one hand, the bottleneck seems to have narrowed technological diversity, leaving behind only the most basic and durable forms. On the other, that very durability may have saved us. The 𝐓𝐈𝐿𝐼𝐴n hand axe was simple enough to be taught, versatile enough to endure, and resilient enough to be rediscovered if lost. Its persistence across hundreds of thousands of years suggests that even in humanity's darkest age, the core of technological tradition held. When numbers collapsed, technology did not collapse completely. It dimmed, it stagnated, but it endured, just as the lineage itself endured. How sure are we that the bottleneck really happened? Modern genetics has given us tools powerful enough to peer back into deep time, far beyond the reach of most fossils or artifacts. From the genomes of living people, scientists reconstruct ancestral populations and infer events that shaped our lineage hundreds of thousands of years ago. One of the most startling findings is that between 900 and 800,000 years ago, the breeding population of our ancestors may have dropped to around 1,000 individuals, clinging to survival for over 100,000 years. Yet not everyone accepts this picture at face value. Numbers do not always speak with one voice, and the further we peer into the past, the more careful we must be in interpreting what they mean. The reveal here lies in how genetic methods work. The finding of a bottleneck comes from analyses of coalescent theory, a branch of population genetics that uses the distribution of gene variants to model the size of ancestral populations. In practice, this means looking at genomes from thousands of people today and asking how often their genetic differences trace back to common ancestors. If diversity is low, it suggests a past reduction in numbers. Using a new method known as 𝐓𝐈𝐌𝐿𝐼, fast infinitesimal time coalescent, researchers in 2023 reconstructed population sizes at unprecedented resolution. The result was the dramatic bottleneck around 930,000 years ago, during which the effective population size plunged to roughly 1,280. The numbers are so stark that they demand attention. But here is where caution enters. An effective population size is not the same as a head count. It refers to the number of breeding individuals in an idealized model. The actual census population may have been higher, since factors like unequal sex ratios or uneven reproduction can reduce effective size. So when we say 1,280, that does not necessarily mean that only that many humans were alive. It means that their genetic contribution was equivalent to a population of that size. Others may have existed but left no descendants, and in genetic terms, it is as though they never lived. Already the number becomes less a simple fact and more an interpretation. There are also debates about timing. Some researchers argue that the bottleneck could have occurred earlier, perhaps closer to 1 million years ago. Differences in how models are calibrated, which mutation rates are assumed, how recombination is accounted for, can shift estimates by tens or even hundreds of thousands of years. Others suggest that the signal might represent multiple smaller bottlenecks rather than one prolonged one. In such a view, populations might have crashed and recovered several times, with the cumulative effect leaving a genetic scar that looks like a single long decline. The genome does not preserve a precise calendar, only patterns of diversity that must be matched to models. The severity of the bottleneck is another point of contention. Did populations truly fall by more than 98%, or is the drop exaggerated by assumptions built into the method? Some critics note that while human genetic diversity is low compared to other primates, it is not uniquely so. Chimpanzees in fragmented habitats also show low variation. Perhaps humans were never as numerous as assumed in the first place, and the apparent crash is partly a mirage. Others counter that the depth and duration of the signal are too strong to dismiss. The debate continues in papers, conferences and laboratories, with no final consensus. It is also worth noting that genetic methods are still evolving. The 𝐓𝐈𝐿 approach is powerful but new, and like all models, it has limitations. It assumes certain population structures and may struggle to account for complex patterns, such as migration between groups or hidden subpopulations. If our ancestors were spread across Africa in semi-isolated pockets, with occasional gene flow between them, the resulting genetic signals might mimic a single bottleneck, even if no such global collapse occurred. Alternatively, a real collapse may have been even worse than the model suggests, masked by later mixing. The point is that numbers are only as reliable as the models that generate them. Yet even with these caveats, the weight of evidence favours some kind of severe contraction. The low diversity of modern humans compared to other great apes is a fact. The difficulty of finding hominin fossils from the interval between 950,000 and 650,000 years ago is another. The match between genetics and the sparse archaeological record, while not perfect, is striking. Critics may question the details, the exact date, the depth of decline, the duration, but few argue that our lineage passed through the middle Pleistocene without serious challenges. The bottleneck, whether precisely as described or in modified form, reflects a real crisis. The haunting part of this debate is what it reveals about the nature of scientific certainty. Numbers seem exact. 1,280 sounds like a fact carved in stone. But in truth, it is a model output, an estimate wrapped in assumptions, a clue rather than a final answer. As humble investigators, we must admit that we do not know whether the true number was a little higher, a little lower, or distributed unevenly across scattered groups. We do not know if the bottleneck began earlier or lasted longer than models suggest. What we know is that our genomes carry the signature of extreme reduction, and that our existence today means those few survivors succeeded against extraordinary odds. The resolution, then, is to hold both confidence and humility together. Yes, the genetic evidence is strong enough to support the idea of a bottleneck. No, it does not tell us everything. Science rarely does. The haunting question remains, if numbers do not lie, why do they leave so much unsaid? What stories of survival, migration, and loss are hidden between the lines of genetic code? The answer is not yet clear, but every advance in methods brings us closer. Until then, the bottleneck is both fact and mystery, a number that shapes our past while reminding us of the limits of what numbers can reveal. Was this the only near-death event for humans? The story of our lineage is not a straight path of expansion and triumph. Even after surviving early crises, humanity has faced repeated contractions, some global and some regional, some severe enough to leave marks in our genomes, others debated to this day. Two of the most striking examples are separated by tens of thousands of years. One involves a volcano in Sumatra around 75,000 years ago. The other is far stranger, a collapse of male lineages only about 7,000 years ago, when cultures and societies were already forming. Together they remind us that bottlenecks are not relics of deep prehistory alone, but recurring features of human existence. The reveal begins with the Toba supereruption. About 75,000 years ago, a caldera in Sumatra exploded in one of the largest volcanic events of the last 2 million years. The eruption ejected thousands of cubic kilometers of ash, spreading fallout across South Asia and Africa. Sulfur aerosols lofted into the stratosphere, reflecting sunlight and cooling the planet. Models suggest a drop in global temperatures lasting years, possibly decades, a volcanic winter on a scale no human has ever witnessed. Some early researchers proposed that this event nearly extinguished our species, reducing the global population to just a few thousand individuals. This idea became known as the Toba catastrophe hypothesis. For a time, the hypothesis seemed compelling. Archaeological sites in India showed thick layers of volcanic ash, suggesting widespread devastation. Genetic studies in the late 20th century found surprisingly low diversity in humans, which some scientists linked to a bottleneck coinciding with the eruption. It seemed plausible that the survivors were those who lived far from the fallout, their descendants spreading later to repopulate the world. But evidence is rarely so simple. Over the past 2 decades, excavations in Africa and South Asia have revealed more continuity than collapse. In southern Africa, sites occupied before and after the eruption show little disruption in stone tool traditions. In India, beneath meters of ash, people appear to have resumed activities quickly. This has led many researchers to question whether Toba truly caused a global bottleneck. The eruption was enormous, but its climatic impacts may not have been as catastrophic as once modelled. Populations may have declined locally, but not globally. Today, the consensus is that while Toba was devastating, it did not nearly wipe us out. The human lineage had already endured other pressures, and this was one more trial rather than the singular brush with extinction it was once imagined to be. If the Toba hypothesis has weakened, another, stranger bottleneck has gained attention: the collapse of Y chromosome diversity about 7,000 years ago. Unlike the deep time bottlenecks, this one is not about volcanic winters or glacial cycles. It is about social structures. Geneticists have found that in many parts of Africa, Europe, and Asia, Y chromosome variation shrank dramatically in the Neolithic and early Bronze Age. For every 17 women reproducing, there seems to have been only one man passing on his genes. The result was a massive reduction in male genetic diversity, visible in the chromosomes of living men today. What could cause such a skew? The most likely explanation is cultural. As societies became more complex, power and status determined who could reproduce. In some groups, a few dominant men fathered many children, while others had none. Warfare may have played a role. Victorious groups often killed or displaced rival males and took their partners. Social hierarchies, polygyny, and violent competition concentrated reproductive success in the hands of a few. The result was a bottleneck not of the species as a whole, but of its male lineages. Women's genetic diversity remained broad, but men's shrank. It was not extinction, but it reshaped the genetic landscape. The haunting part of these examples is how different they are. Toba was a natural catastrophe, a volcanic explosion indifferent to human lives. The Y chromosome collapse was human-made, the result of cultural patterns, conflict and inequality. One shows the vulnerability of humans to the planet's forces, the other shows our vulnerability to ourselves. Both leave marks in our DNA, reminders that bottlenecks can arise from very different causes. These other bottlenecks also highlight the challenge of interpretation. Numbers alone cannot tell us the whole story. The low diversity observed after Toba could be explained by earlier reductions. The Y chromosome collapse could be a global phenomenon or the sum of many regional events. Science continues to refine these pictures, debating whether we are looking at true catastrophes or the artifacts of incomplete data. The debates themselves show that bottlenecks are not simple events but complex intersections of biology, environment, and culture. The resolution is not that we can map every population crash with certainty, but that bottlenecks are part of the human condition. They remind us that survival is fragile and continuity uncertain. We are not the result of steady progress, but of repeated contractions and expansions, each shaping the path forward. The haunting question is whether more such bottlenecks lie ahead. Natural disasters, pandemics, and social upheaval still threaten to reduce populations or genetic diversity. The past shows us that near-death experiences are not anomalies but recurring trials. The fact that we are here today means that our ancestors survived them. Whether we will survive future ones remains unwritten. Are we immune to extinction now, or just more fragile in new ways? Looking back at the long story of our species and its ancestors, it is tempting to believe we have outgrown the possibility of collapse. After all, there are over 8 billion of us today. We occupy every continent, control vast amounts of energy, and reshape landscapes and ecosystems at will. But survival has never been about numbers alone. The past teaches us that even large populations can be vulnerable when environments shift quickly or when interdependence makes systems brittle. The question is not whether humanity could vanish in the same way it nearly did 900,000 years ago, but whether new conditions of fragility now surround us. The reveal begins with climate. Then as now, climate change was a central driver of survival. Today the cause is different, not orbital cycles, but the accumulation of greenhouse gases from human activity. Yet the effects echo the past. Temperatures are rising, ice sheets are melting, and weather extremes are becoming more frequent. Unlike the slow transitions of the Pleistocene, the present warming is happening on the scale of centuries rather than tens of thousands of years. Species, Ecosystems and societies have less time to adapt. Could climate change alone bring humanity to the brink? Most scientists would say unlikely in the immediate sense. Humans are adaptable, and global agriculture and technology buffer against local failures. Yet climate shifts already displace millions through drought, floods, and rising seas. If warming accelerates, it could strain food systems and water supplies, leading not to extinction but to fragmentation and conflict. The danger is not sudden erasure but the slow erosion of stability, where survival is still possible, but harder for many. Another shadow is nuclear war. Since the mid-20th century, humanity has carried the means of its own destruction. A full-scale exchange of nuclear weapons would not only kill millions directly, but inject soot into the stratosphere, cooling the planet in a so-called nuclear winter. Crops could fail, ecosystems could collapse, and survivors would face starvation. Unlike the volcanic eruptions of the past, this is a catastrophe of our own making. Could it reduce populations to a fraction of what they are today? Yes. Would it mean extinction? Not necessarily. Humans are widespread and diverse, and some groups would almost certainly survive. But the risk is not negligible. Our own technology has become one of the greatest threats to continuity, proof that fragility can grow with power. Pandemics remind us of another vulnerability. For most of history, disease has been local, spreading slowly between communities. Today, global travel allows pathogens to circle the planet in days. The COVID-19 pandemic was a glimpse of how interconnected we are, and how fragile those connections can be. It was not an extinction threat, but it showed how a single virus can destabilize societies, economies, and daily life. Could a more lethal pathogen do worse? Yes, in principle. Yet here too humans have advantages: modern medicine, rapid communication, and coordination. We are more vulnerable to global spread, but also more capable of global response. Again, the danger is not total extinction but serious reduction and disruption, echoing smaller bottlenecks of the past. Environmental collapse poses a quieter threat. Humans depend on ecosystems for food, water, and air, yet biodiversity is declining at an unprecedented rate. Pollinators, fisheries, forests, all are under strain. In the short term, technology substitutes for some losses, but long-term erosion of ecological foundations could leave us more fragile. Our ancestors endured bottlenecks when prey vanished or habitats shrank. We now face similar risks at a planetary scale, but this time we are both the victims and the agents of change. The haunting question is whether size itself is protection. With billions alive, surely some would endure almost any catastrophe. That is true. It is difficult to imagine an event that could erase humanity entirely in the near term. Even nuclear war or global pandemics would likely leave scattered survivors. But survival is not the same as flourishing. A population reduced to a fraction, fragmented and vulnerable, would still face the same uncertainty as our ancestors did in the past. The continuity of knowledge, culture, and civilization could be broken. The lesson of Bottlenecks is that survival alone is not guaranteed progress. It can mean long ages of scarcity, stagnation, and vulnerability. We must also ask whether modern interdependence makes us more or less resilient. Ancient humans lived in small, scattered groups. Collapse in one region did not mean collapse everywhere. Today, our food systems, supply chains, and energy networks are global. This allows abundance, but also creates fragility. A disruption in one place can ripple worldwide. In this sense, we may be more vulnerable than small groups of foragers were. We cannot easily retreat into local refuges if the systems we depend on unravel. The resolution here is not alarmism, but humility. Humanity is not immune to bottlenecks. We have escaped some of the limits of the past, but we have created new ones. Climate change, nuclear war, pandemics, and ecological collapse are not prophecies but possibilities. Science cannot say whether they will happen, only that the risks are real. What history shows us is that survival is never permanent. Every species faces trials, and some fail them. The haunting question is whether, if faced with our own bottleneck again, we would have the resilience to endure as our ancestors did 900,000 years ago. Would the knowledge we carry be enough, or would it fracture in the ruins of our systems? We cannot know. But we can learn from the past that numbers do not make us invincible, and fragility often hides in strength. What did it mean that almost all of us were a race before we were us? To look back 930,000 years is to confront a paradox. We are accustomed to thinking of humanity as expansive, inventive, and inevitable. Yet the evidence from genetics tells us there was a time when we were anything but inevitable. For more than 100,000 years, the ancestors of humans teetered on the edge of disappearance, reduced to perhaps a single community's worth of survivors. The scale is hard to grasp. Every living human being today may descend from no more than 1,000 or so individuals who endured through that dark interval. If their luck had faltered, if storms or droughts or predators had overwhelmed them, there would have been no us. The story of our species would have ended before it began. The reveal of this realization is humbling. It strips away the illusion of inevitability. For much of Earth's history, humans were fragile, local, and dependent. We were not masters of fire or builders of civilizations. We were scattered primates, struggling to find food and shelter in a world that was colder and harsher than our bodies were built for. We had no guarantee of survival, no certainty that the next season would not be our last. The bottleneck is a reminder that survival often comes down to chance as much as adaptation. Perhaps a few groups lived near water sources that did not dry up. Perhaps they happened upon regions where prey animals lingered. Perhaps they built shelters that blunted the wind or cooperated in ways others did not. Whatever the reason, they endured while others vanished, and their endurance became our inheritance. What was lost in that erasure? We cannot know. Entire lineages of humans disappeared, leaving no descendants to carry their genes or their traditions. Innovations in tools, strategies for hunting, or social customs may have flickered briefly, and then died with the groups who carried them. The fossil and archaeological record is nearly silent, offering only fragments. The silence itself is part of the loss. We know there were others who walked the earth then, cousins and rivals, and we know many of them did not survive. Their stories ended in obscurity, their ways of life erased from memory. Extinction does not only erase bodies, it erases knowledge, perspectives, and possibilities. And yet, what was carried through is equally profound. From those 1,000 or so survivors came all of us. Every language, every culture, every painting on cave walls, every poem and equation and song, all of it traces back to people who endured when numbers had collapsed to almost nothing. Their survival was not heroic in the way we often tell stories. They were not conquerors. They were simply persistent. They ate what they could find, sheltered as best they could, and bore children who lived long enough to repeat the cycle. In that persistence lay the seed of everything that followed. It is tempting to ask what it felt like to be alive then. Did those survivors know they were few? Likely not. Their world was bounded by the horizon, their communities by the small circles of kin they lived with. They would not have seen themselves as remnants of a dying lineage, but simply as people, struggling as people always do. The enormity of their situation is visible only to us, looking back with tools of genetics and geology. They did not know they carried the weight of the future, and perhaps that ignorance was merciful. What meaning do we take from this near erasure? One lesson is that survival itself can be enough. We often measure human value in terms of art, technology, or conquest. But in the darkest times, the act of simply continuing mattered more than anything else. The survivors of 930,000 years ago may not have painted or sung or built, but they kept living. That persistence was the foundation for everything that came later. There is comfort in this scale of history. We are here not because of inevitable progress, but because ordinary lives were strung together without interruption for hundreds of thousands of years. Another lesson is humility. To know that all of us descend from such a small remnant is to realize how fragile the line of continuity is. We are not the product of endless expansion, but of narrow survival. We're here by chance, by luck, by resilience, and by circumstance. The haunting question is what futures were lost when so many did not survive. Would other human lineages have developed different forms of culture or technology? Would the world have been richer if more ancestors had endured? We cannot know. We can only live with the fact that history narrowed and we are the result of what was left. The resolution is not despair but perspective. To see our species almost erased is to recognize that survival itself is extraordinary. The worst time to be human was also the time that defined us. Through that crucible, our lineage was tested and reduced, but not extinguished. We carry both the scars and the legacy of that trial. Every person alive today is proof that the line held, however tenuously. There is comfort in that, especially in moments when the present feels uncertain. We have endured worse than we often imagine. What did it mean that almost all of us were erased before we were us? It meant that humanity was never inevitable, only contingent. It meant that survival was not guaranteed, only achieved through persistence. And it meant that everything we are today was carried through a bottleneck by a few thousand fragile beings who could not know what they were preserving. The haunting question is whether we honour that inheritance, not by avoiding extinction forever, for no species can, but by recognising the miracle of continuity while it lasts. To know that we exist at all is to know that even the worst time to be human did not end us. That knowledge, humbly held, may be the deepest comfort history can offer. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.